Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. In the silent depths of space, there are wanderers. From the faintest dawn of history, human eyes gazed upward at bright points of light that moved against the fixed stars. The ancients called them planets, meaning wanderers, imagining gods and myths trailing across the night sky. But beyond the poetry of ancient minds, what truly is a planet? It is more than a mere light in the sky. It is a world unto itself. Planets are the great wanderers of the cosmos, worlds shaped by fire, gravity, and ice, each with its own story, written in molten rock and swirling cloud, in howling wind and drifting snow. They are the children of stars, born from cosmic dust and pulled into spheres by the inexorable embrace of gravity. They orbit in darkness, illuminated only by the suns they circle, and yet each holds its own internal light. The warmth of formation or radioactive decay, the glow of volcanoes, the electric crackle of storms. They range from scorching spheres of rock to bloated giants of gas, from oceanic blue orbs to frozen balls of ice and stone. Some are ensconced in thick blankets of cloud, others naked under the cosmic night. Some, incredibly, are lonely nomads, drifting between stars with no sun to call home, true wanderers in eternal night. To be a planet is to dance in a delicate balance. It means to circle a star in a cosmic rhythm, held by gravity's tether yet ever, falling around the light. It means to be round, sculpted into a globe by one's own gravity, mostly smooth, yet often scarred by the battering of eons. It means to dominate a little corner of space, clearing a path through smaller debris. Planets come in families, solar systems, where each member plays its part in the celestial choreography. Our own family is the solar system, with the sun as the patriarch and planets as its heirs, moving in regal procession. Imagine drifting high above the plane of our solar system. Below, the sun burns as a golden beacon, and around it, like marbles on invisible tracks, the planets sweep through space. Mercury, closest to the sun, is a little burnt cinder racing along its tight orbit. Venus follows, wreathed in thick, toxic clouds reflecting sunlight like a jewel, hiding hellish heat beneath. Earth, our home, blue with oceans and white with clouds, teems with life, our oasis in the dark. Mars comes next, a ruddy desert with ghostly dust storms and polar caps of frost, whispering of a wetter past. Far beyond, a belt of asteroids forms a rough boundary, and then the giants take the stage. Jupiter, king of planets, streaked in bands of stormy color, guards a menagerie of moons. Saturn, with its shimmering rings of ice, elegant and enigmatic. Uranus, tipped on its side, rolling around the sun with a pale cyan hue. Neptune, deep blue and distant, where supersonic winds drive dark storms. And at the edge, small icy worlds like Pluto circle in shadow, blurring the line between planet and comet in the distant Kuiper belt. These are the known members of our Sun's family, 8 major planets by the modern definition, and a host of dwarf planets and countless smaller bodies. Yet planets are not unique to our Sun. As our knowledge grew, we discovered planets orbiting other stars by the thousands. We realized our night sky is filled with other suns, each with their own retinue of worlds. Planets, it turns out, are abundant in the galaxy. Perhaps every star has at least one, and in total, they likely number in the trillions. Some of these exoplanets are familiar in outline, rocky Earth-like bodies or gas giants like Jupiter, but others are stranger than we ever imagined. Giants so close to their stars that their skies rain molten iron, or worlds locked in eternal ice, far from any warmth. There are even worlds that wander alone, rogue planets drifting in perpetual darkness, having been thrown free from their stellar birthplace. The cosmos is literally overflowing with planets of every kind, each a chapter of the grand story of creation. This journey will explore what it means to be a planet from multiple angles. We will trace the historical path, from ancient stargazers to the scientific revolution that revealed Earth as a planet, and the later discoveries of Uranus, Neptune, and Pluto's reclassification, a saga that redefined our cosmic perspective. We will visit the inner solar system, the terrestrial planets, small spheres of rock scorched or nurtured by the sun, each with a unique personality. Mercury's extreme heat and cold, Venus's runaway greenhouse inferno, Earth's living biosphere, and Mars's lost rivers and thin air. Then we venture to the outer solar system, colossal gas and ice giants with raging storms and delicate rings, and moons that might hide life beneath their icy crusts. We will meet the dwarf. Planets like Pluto, Eris, and Ceres, diminutive worlds that challenge our definitions and remind us how diverse planets can be. Beyond visiting each member of our solar family, we will delve into the processes that shape all planets. We'll witness towering volcanoes that spew fire and shifting tectonic plates that mold the lands. We'll examine impact craters, the scars of cosmic bombardment, and winds and water that erode and change landscapes over eons. We'll peer into atmospheres thick and thin, the crushing yellow haze of Venus, the thin cold sky of Mars, Jupiter's banded clouds, and Titan's orange smog. We'll experience weather and climate extremes beyond any earthly storm, from Jupiter's great red spot that has raged for centuries to the 1,200 mile-per-hour winds of Neptune that whip methane clouds into streaks. We will also uncover the hidden magnetic fields and internal structures that many planets possess. Those invisible shields born from molten cores or metallic hydrogen that can deflect deadly solar winds, and the strange interiors where pressures soar and matter behaves in exotic ways. And as our voyage extends outward, we will leave the comfort of our solar system entirely to discover exoplanets in their astonishing variety. We'll classify these alien worlds, super-Earths, hot Jupiters, mini Neptunes, rogue planets, and more, and see how they broaden our understanding of what a planet can be. We'll ponder the conditions that might make a planet habitable, able to support life, and how scientists seek the faint fingerprints of biology on worlds light years away. Finally, we'll look ahead to future exploration, the upcoming missions and bold ideas to visit new worlds, to send robot emissaries or even humans to planets and moons, and to build telescopes capable of reading the atmospheres of Earth like planets around distant suns. And throughout this odyssey, we will reflect on philosophical questions. What do these diverse worlds teach us about our own existence? How has the study of planets changed the way we see ourselves and our place in the universe? In exploring alien worlds, we inevitably hold up a mirror to Earth and to humanity. So, let us begin where our ancestors once did, by seeking to understand the wandering lights in the sky, and in doing so, embark on a journey across the solar system and beyond. Our first stop is the story of how we came to know these planets at all, a tale of curiosity, observation, and the courage to question our place among the stars. From myth to discovery, a history of our understanding. For most of human history, planets were points of light, their true nature unknown. In antiquity, 5 wanderers were known: Mercury, Venus, Mars, Jupiter, and Saturn. These wandering stars were held as gods. Mercury was the quick-footed messenger, Venus the goddess of love, shining as morning and evening star, Mars the blood, red warrior, Jupiter the king of heaven, and Saturn the god of time. The sun and moon were counted among the planets in the old world view, and Earth was not a planet at all, but the fixed center of creation. In ancient Greece and Rome, And in civilizations as far-flung as Babylon, India, and China, elaborate cosmologies placed these 7 wanderers on crystal spheres or chariots circling the Earth. Their motions were mysterious but meticulously observed. Occasionally, Mars would retrograde, moving backward against the stars, confounding expectations. To ancient astronomers, the planets were divine oracles whose motions foretold omens and seasons, yet their physical nature remained a subject of philosophical speculation. Aristotle and Ptolemy believed in a geocentric cosmos, the planets, sun and moon revolving in perfect circles around an unmoving Earth. It took bold imagination and careful observation to break this geocentric spell. In the 16th century, Nicholas Copernicus proposed a revolutionary idea. The sun, not Earth, was the center, and Earth itself was just another planet circling the sun. This heliocentric model demoted Earth from its special pedestal and made it one of the wanderers. It was a radical, even heretical thought at the time, challenging both scientific and religious dogma. But evidence soon began to accumulate. In 1609, Galileo Galilei turned the newly invented telescope to the heavens and witnessed wonders that forever changed our understanding of planets. He saw that Venus goes through phases like the moon, waxing and waning in shape, which only made sense if Venus orbits the sun, not Earth. He discovered 4 moons circling Jupiter like a miniature planetary system, a clear sign that not everything revolved around Earth. And he observed the rugged mountains and craters on our moon, showing celestial bodies were not perfect ethereal orbs, but had landscapes and geology. Galileo's telescopic revelations gave tangible reality to planets as worlds, places that could be seen and studied, not just lights. With the Copernican paradigm taking hold, astronomers realized that Earth was a planet too, moving through space with the rest. This was a profound philosophical shift. Humanity had to accept that our world was one among many. Over the next centuries, the solar system's known architecture expanded. In 1781, William Herschel, scanning the sky with a powerful telescope, noticed a tiny disk rather than a point. He had accidentally discovered Uranus, the first new planet found in recorded history. At first, Herschel thought it might be a comet, but its slow, steady orbit revealed it as a planet beyond Saturn. The solar system now had 7 planets. The discovery of Uranus doubled the size of the known solar system and suggested there could be more unseen worlds farther out. Uranus's orbit itself held clues of something more. By the early 19th century, astronomers noticed Uranus did not move exactly as predicted. It was being subtly tugged by an unknown force. 2 mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated that an 8th planet must be lurking farther out, its gravity perturbing Uranus's path. In a triumph of physics and astronomy, Neptune was discovered in 1846, almost exactly where the calculations predicted, by Johann Galle and Heinrich Darest at the Berlin Observatory. Neptune was dim and distant, invisible to the naked eye, yet the power of human reasoning had brought it to light. Now the known planetary count was 8. Around the same period, another kind of planet was found in the gap between Mars and Jupiter. In 1801, Giuseppe Piazzi discovered Ceres, a small world orbiting where a much larger planet might have been expected. Soon, Pallas, Juno, and Vesta were found, more small bodies in that zone. At first, Ceres was called a planet, but as dozens more of these objects were detected, it became clear that Ceres was the largest of a whole belt of minor planets, not a lone new world on par with the others. By the mid-19th century, school textbooks briefly swelled the planet count to as high as 11, only to drop back down as Ceres and its kin were reclassified as a separate category. The word planet came to be reserved for the major bodies that dominated their orbits. By the turn of the 20th century, the solar system's 8 primary planets were well known, but some astronomers suspected there might be yet another planet lurking beyond Neptune, Planet X, as it was dubbed. Percival Lowell, an American astronomer, hunted for this theoretical planet in the early 1900s, driven by hints of irregularities in Neptune's motion. Lowell did not find it, but after his death, the search continued at Lowell Observatory in Arizona. In 1930, a young astronomer named Clyde Tombaugh systematically photographed the star fields of the ecliptic and painstakingly looked for anything that moved. On a cold February day, Tombaugh found a dim speck that shifted position against the stars. It was the long-sought planet X, soon named Pluto, after the Roman god of the underworld. The public was enthralled. Pluto was hailed as the 9th planet, a tiny, distant oddball in the solar system's outer reaches. For much of the 20th century, the solar system was taught as 9 planets, Mercury through Pluto. But as telescopes improved, especially towards century's end, we began to find more objects orbiting out near Pluto. In 1992, the first of many Kuiper Belt objects was discovered not far from Pluto's orbit, implying Pluto was not a lone maverick, but part of a larger population of small icy worlds. The trickle of discoveries became a deluge in the 2000s. Then, in 2005, astronomers announced Eris, an object about as large as Pluto, far beyond Pluto's orbit. Suddenly, our neat conception of the solar system was challenged. If Pluto was a planet, why not Eris? And what about the other large Kuiper Belt objects like Makemake and Haumea being found? The field reached a crossroads. In 2006, the International Astronomical Union took a vote in a meeting that echoed around the world. They formally defined the term planet for the first time. According to the IAU, a planet must orbit the Sun, be massive enough for its gravity to pull it into a nearly round shape, and have cleared the neighborhood around its orbit. By that definition, Pluto failed the third criterion, since it shares the outer solar system with many similar icy objects. Pluto was reclassified as a dwarf planet along with Eris and Ceres. Overnight, the solar system went from 9 planets to 8. The decision was contentious. Many in the public lamented the demotion of Pluto, and even some astronomers disagreed, pointing out that Earth, Jupiter, and others still have small neighbors in their orbits. The debate over what constitutes a planet continues philosophically, but in practice, the new terminology stuck. We now speak of the 8 classical planets and a growing menagerie of dwarf planets. This historical journey, from the earliest recognition of wandering stars, to the Copernican revolution that made Earth a planet, to the telescopic discoveries of new planets, and finally to the reclassification of Pluto, shows how our understanding of planets has evolved with our knowledge. We moved from an Earth-centered universe to a Sun-centered solar system, and then to a vision of countless solar systems in our galaxy. Each step required us to redefine our place in the cosmos, and even as we debated definitions, we learned that nature resists rigid categories. Planets come in a continuum of sizes and orbits. The line between planet and not planet can be blurry at the edges. The story of how we came to know the planets is a story of curiosity, persistence, and a willingness to change our perspective when confronted with new evidence. Having placed ourselves among the planets and traced their discovery, we now turn to explore the planets themselves as worlds. We begin with the inner solar system, those rocky neighbors of Earth that bask closest to the Sun's fire. The inner worlds: Mercury, Venus, Earth, and Mars. We begin our planetary journey with the inner solar system, a realm of sun, baked rocks, and metal. These are the terrestrial planets, small, dense, and composed mostly of silicate rock and iron. Born of similar materials, and initially not so different, they have since diverged into 4 dramatically distinct worlds. From airless craters to runaway hothouses to a living blue oasis and a frozen desert, the inner planets show how varied outcomes can be even among sister worlds. Mercury, the closest planet to the Sun, is a little grey furnace of extremes. It is the smallest of the 4 inner planets, only slightly larger than our Moon. Like the Moon, Mercury's surface is heavily cratered and ancient, recording a violent history of impacts. There are brilliant ray crater patterns splashed across its dark grey terrain and enormous basins from asteroid collisions long ago. Mercury has almost no atmosphere, just a whisper of atoms blasted off its surface by the sun's radiation, so nothing shields it from meteoroids or evens out its temperature. Daytime on Mercury is blistering, hot enough to melt lead, but the night plunges into frigid darkness since there is no substantial air to trap the heat. A Mercurian day lasts 2 Mercury years long, because Mercury rotates slowly and orbits fast. This results in oddities. If you could stand on Mercury's surface, you would see the sun blazing huge in the sky, rising and setting in a slow, drawn-out dance, even briefly reversing course around sunrise due to Mercury's orbital resonance. Inside, Mercury is a world that punches above its weight. Despite being so small, it is incredibly dense, almost as dense as Earth, because it contains a gigantic iron core occupying most of its interior. This core, spanning about 3/4 of the planet's diameter, generates a magnetic field around Mercury, albeit a feeble one only about 1% as strong as Earth's. Still, it's remarkable that this tiny, slowly rotating planet maintains any magnetic field at all. Mercury's iron heart also hints at a dramatic birth. Perhaps it formed from normal proportions of rock and metal, but a titanic impact early on stripped much of its rocky mantle away, leaving a metal, rich remnant. On Mercury's surface, the evidence of an active past includes long scarps and cliffs, some hundreds of kilometers long and soaring up to a mile high, that crisscross the terrain. These formed as Mercury's core and mantle cooled and contracted, wrinkling the crust above. Volcanic plains, now solidified, also exist, indicating that billions of years ago, lava once flowed across Mercury's surface. But for at least the last few billion years, Mercury has been geologically quiet, a bare, inert world of extremes. It is a planet essentially without air or water, where the landscape is carved only by impact and the slow thermal cracking of sun-baked rocks. In the brilliant morning sun, the ground would be blinding and dead silent, and at night, the stars would burn cold in a black sky over a landscape as still as a tomb. Leaving little Mercury and moving outward, we encounter Venus, often called Earth's twin in size and composition, but in reality, a twisted mirror image of Earth, similar in bulk, yet utterly hellish in condition. Venus is almost exactly the same size as Earth and formed in the same neighborhood of the Sun, presumably with similar ingredients. It likely started out much like Earth, with volcanoes, a thick atmosphere, and possibly even oceans. But at some point, Venus took a divergent path and fell victim to a runaway greenhouse effect. Today, Venus is a world enshrouded in dense, yellowish cloud, its surface hidden from view in visible light. That thick atmosphere is composed overwhelmingly of carbon dioxide, with clouds of corrosive sulfuric acid droplets whipping around the planet. The weight of Venus's atmosphere is enormous. At the surface, the pressure is about 92 times that of Earth's sea level. This heavy blanket has trapped so much heat that Venus's surface is the hottest in the solar system, around 464 degrees C everywhere, day or night, pole or equator. It is hotter even than Mercury, despite being nearly twice as far from the Sun, solely because of the greenhouse gases that lock in the Sun's heat. In essence, Venus shows what happens when a planet's heat balance goes awry. Sunlight passes through the clouds, heats the surface, and the infrared heat cannot escape efficiently due to the CO2, causing a feedback loop of warming. Long ago, Venus might have had temperate conditions, but as the Sun grew brighter over eons, Venus's oceans likely evaporated, and water vapor helped drive temperatures up until the ground itself baked out carbon dioxide from rocks, filling the air with CO2 and turning the planet into a pressure cooker. If you could descend through Venus's clouds, you would find the light growing dim and orange, tinted by the sulfuric haze. By the time you reached the ground, it would be twilight at midday, and the air would be a toxic yellowish fog, so thick it feels almost like a fluid. The heat would be instantly overwhelming, high enough to melt lead, and certainly high enough to melt any lander electronics within an hour or two. The landscape, as revealed by Soviet Venera landers and radar mapping from orbit, is a rolling desert of orange, red rocks, and vast volcanic plains. Venus's surface has mountains higher than Everest and great plateaus, as well as thousands of volcanoes, from huge shield volcanoes to innumerable small cones. The terrain has strange features called coronae, circular patterns hundreds of kilometers wide, believed to be caused by upwellings of magma pushing on the crust. Yet surprisingly, there are few impact craters. The relative lack of craters tells us Venus's surface is geologically young, maybe only 500 million years old. Planetary scientists suspect that Venus underwent a global resurfacing event, perhaps massive volcanism that paved over older terrain, and it may still be volcanically active today. In fact, recent studies of old radar images have shown hints of change in some calderas, suggesting an ongoing eruption, and the Venusian atmosphere contains mysterious chemistry hinting at active volcanoes. However, Venus has no plate tectonics like Earth. Its crust appears to be one giant stagnant lid, which might periodically break down in outbursts of planet-wide volcanism, essentially repaving the planet in floods of lava. Beneath the surface, Venus likely has a metallic core and a mantle similar to Earth's, but unlike Earth, it spins extremely slowly. A Venusian day is 243 Earth days, and curiously, it spins backwards. This sluggish rotation is likely one reason Venus has almost no magnetic field. Without a protective magnetosphere, the upper atmosphere of Venus is constantly bombarded by the solar wind, which slowly strips away lighter molecules. Yet the atmosphere is so thick and heavy that losing some particles to space hardly dents it. Standing on Venus, you would experience a bizarre scene, a dim orange glow in all directions through the haze, the air utterly still near the ground, and a forbidding, silent landscape of rocks and gently sloping volcanic plains. It is an infernal environment, the closest thing to a vision of hell on any planet, and a stark warning of the power of atmospheric chemistry gone wrong. Traveling onward, we arrive at our own planet, Earth. It might seem unnecessary to describe Earth among its neighbors, but viewing Earth as a planet, one of many, is key to understanding what makes it special. Earth is the only planet we know of that hosts life, and not just a few microbes, but a rich biosphere of complexity and diversity, including us, who can marvel at that fact. Several factors conspire to make Earth a haven amid the void. It orbits in the habitable zone of the Sun, where temperatures allow liquid water to persist on the surface. Our planet is just large enough to hold on to a substantial atmosphere, but not so large as to become a gaseous giant. Earth's surface is a mosaic of blue oceans, green and brown continents, and white clouds, a dynamic, ever-changing patchwork, sculpted by both geological forces and living organisms. Unlike the rest of the inner planets, Earth's crust is divided into moving plates, an evolving jigsaw puzzle riding atop the slow churning of the mantle. This plate tectonics is a geological wonder. Continents drift, collide, and separate. Earthquakes rumble along faults. Volcanoes emerge where plates diverge or converge. Over millions of years, this process rejuvenates the surface, builds mountains, and recycles carbon, and may be crucial in regulating Earth's climate over geologic time. Indeed, plate tectonics, with its ability to bury carbon, rich sediments, and then release CO2 via volcanoes, acts as Earth's thermostat, keeping temperatures within a range that allowed oceans to remain liquid for billions of years. Earth's atmosphere is a unique mix: 78% nitrogen, 21% oxygen, plus traces of other gases like argon, carbon dioxide, and water vapor. That oxygen is a direct product of life. Photosynthetic organisms have been exhaling it for eons. The atmosphere is dense enough to buffer the surface from small meteoroids and to distribute heat around the globe, but thin enough that our planet isn't smothered in crushing pressure. It gives us a mild greenhouse effect, enough to keep the oceans from freezing solid, but not a runaway like Venus. And it shields us from deadly solar and cosmic radiation, especially thanks to Earth's magnetic field. Generated by a rotating, convecting liquid iron core, our magnetic field forms a protective bubble that deflects charged particles from the sun. Where some of those particles do leak through near the poles, Earth offers a dazzling light show, the auroras shimmering green and red in polar skies. Earth's magnetic field, plate tectonics, and moderate atmosphere all work in concert with the sun's favorable distance to create a stable, life-friendly environment. In that stable environment, water could remain liquid and life could take hold. Life, in turn, transformed the surface and air, covering once barren rock with soil and foliage, and pumping out oxygen to create an ozone layer protecting the surface from ultraviolet rays. From space, Earth is a shimmering blue marble with swirling white weather systems, a striking contrast to the monotonous clouds of Venus or the rust, red dust of Mars. Yet, early in its history, Earth might have looked more like those worlds in some ways. The young Earth's atmosphere had no oxygen and was rich in carbon dioxide and methane. The surface was largely molten at first and heavily bombarded by asteroids, pockmarking it like Mercury. But Earth cooled, oceans formed, life arose, and life's presence terraformed the planet into the benign paradise we now cherish. Earth's geology and biology are deeply intertwined. It is the only planet known where rocks breathe and living creatures move mountains. While Earth has its share of extreme environments, from Antarctica's icy wastes to the Sahara's furnace sands, it remains the gentlest of the inner planets, blessed with liquid water and a breathable sky. It is, simply put, home. And as we study the other planets, we constantly hold Earth as the reference, asking, why is this planet dead or boiling while Earth thrives? The answers inform our understanding of climate, habitability, and the delicate balance that makes our world livable. Stepping away from Earth, we venture back into harsher realms. Mars, the fourth planet from the Sun, has long captured human imagination as a possible abode of life, or at least as a world most similar to our own. It is often called the Red Planet for its reddish-orange hue when seen in the sky, a color due to iron oxide dust coating much of its surface. Mars is about half Earth's diameter and only 1/10 its mass, a modest world that has undergone dramatic change over time. Today, Mars is a cold, dry desert planet. Its atmosphere is a thin envelope of carbon dioxide at less than 1% the pressure of Earth's, essentially a tenuous sky that offers little insulation or protection. Daytime temperatures on Mars near the equator in summer might rise to a balmy 20 degrees Celsius, but at night they plummet far below freezing. At the poles in winter, carbon dioxide from the air freezes directly onto the surface as dry ice, forming seasonal polar caps that sublimate when spring returns. This leads to large seasonal pressure swings and even causes the atmosphere to shift mass between hemispheres, driving global winds. Mars wasn't always so barren. Ancient Mars was more Earth, like all the evidence we've gathered from orbiters, landers, and rovers tells us that billions of years ago, Mars had liquid water flowing on its surface. NASA's rovers have driven through dry riverbeds and studied layered rocks that formed in long, vanished lakes. We have seen branching valley networks etched into the highlands, immense outflow channels gouged by catastrophic floods, and mineral deposits that only form in the presence of water. Mars today has water too, but it's mostly locked up as ice in the polar caps or underground, and a tiny amount as vapor in the atmosphere. What happened? Mars's grip on its atmosphere weakened over time. Being smaller, Mars lost heat faster than Earth, its once molten core partially solidified, and the global magnetic field that might have existed early on dwindled away. Without a strong magnetosphere, the solar wind gradually stripped off the atmosphere. Air pressure fell, temperatures dropped, and surface water either froze or escaped into space. Volcanoes on Mars likely vented gas and lava for a time, perhaps providing temporary warmth, but volcanic activity too has waned. The youngest lava flows on Mars are tens of millions of years old, and no eruptions have been observed in modern times. Still, Mars is not entirely static. It has weather. Thin as it is, the atmosphere can stir up winds that raise reddish dust into towering dust devils that dance across the plains, and occasionally into planet-wide dust storms that can shroud the entire globe in haze for weeks. Its sky often has a butterscotch hue due to fine dust suspended in the air. Wispy clouds of water ice occasionally appear, and at dawn and dusk they can catch the sunlight, creating delicate pastel streaks in the Martian sky. Mars also has seasons, similar in cause to Earth's. In spring and summer, the polar CO2 ice caps partially evaporate, exposing underlying water ice. In winter, they grow as CO2 snow falls. On a Martian summer day, you might see frost that formed overnight glinting in the morning sun, or even a hazy, localized dust cloud that could be analogized to a Martian rainstorm of dust. The Martian surface is a study in contrasts. There are immense shield volcanoes on the Tharsis Bulge that dwarf any on Earth. Just off Tharsis lies Valles Marineris, a canyon system so vast it would stretch across the entire United States, up to 4,000 kilometers long, 200 kilometers wide, and 7 kilometers deep. This Grand Canyon of Mars likely started as a tectonic crack when Tharsis uplifted, then was widened by landslides and perhaps erosion. Elsewhere, the northern hemisphere of Mars consists mostly of rolling, lower plains, whereas the southern hemisphere is high, cratered highlands, an indication that something created a dichotomy in Mars's crust ages ago. Scattered across Mars are impact craters of all sizes, some hosting dune fields within them, others showing gullies on their walls that hint at past flows of water or CO2 ice. Unlike the Moon or Mercury, however, Mars's craters often look worn down, softened by wind, blown dust, or perhaps by ice action. There are also curious features, like the mysterious recurring slope lineae, dark streaks on some crater and canyon walls that grow in warm seasons and fade in cold, once thought to be brine flows. Despite its harshness, Mars remains the most potentially habitable planet after Earth. It is cold, but not beyond the tolerance of life. In fact, hardy microbes on Earth survive in Antarctic ice and dry valleys that resemble Mars. It has water ice in abundance, and perhaps liquid water brines occasionally trickling just beneath the surface. In recent years, tantalizing detections of methane in Mars's atmosphere have stirred excitement, since methane can be a byproduct of microbial life. The dream of life on Mars is one of the reasons we have sent so many probes there. From the Viking landers in the 1970s to the latest Perseverance rover drilling samples for a future return to Earth, we have been reading Mars's history like a book written in rock. That story appears to include a long, gone epoch of rivers and lakes, a gradual climate catastrophe, and the transformation into the cold desert we see now. Mars today is a time capsule of planetary evolution, showing us what can happen when a world's fortunes turn for the worse. Its once thick atmosphere is mostly gone. Some of it lies frozen at the poles, some in the ground, and some atoms still drift in space as a tenuous corona around the planet. In some, the inner solar system presents 4 different fates for terrestrial planets. Mercury is an airless, baked rock, a planet stripped to its core. Venus is a suffocating hothouse under perpetual clouds. a planet where the greenhouse effect ran rampant. Earth is a balanced, vibrant world, a planet just right for liquid water and life. Mars is a once potential Earth that fell into cold desolation, a planet that lost its warmth and air. These worlds teach us about volcanism, climate, and habitability by comparison. Why did only Earth end up with lush oceans and a breathable sky? The inner planets hold the clues in their craters, rocks, and atmospheres. As we leave Mars and venture beyond the asteroid belt, the sunlight fades and an entirely different kind of planet emerges. Titanic worlds of gas and ice, where swirling storms could swallow continents and rings of dust and ice trace cosmic harmonies. Let us now step into the realm of the giant planets, where extremes reach a new level and moons become worlds of their own. Giants of the outer solar system: Jupiter, Saturn, Uranus, Neptune. Passing beyond the asteroid belt, the sun's warmth diminishes and the worlds undergo a dramatic change. Here lie the giant planets, titans composed mostly of gas and icy fluids, with no solid surface to stand on. They dwarf the rocky inner planets in size and mass. Each is like a miniature solar system unto itself, with rings and moons forming complex families. They are planets of colossal storms, deep mysteries, and delicate rings, where the simple word surface loses its usual meaning. Jupiter is the colossus of our solar system, the fifth planet from the Sun, and by far the largest. With a diameter of about 143,000 kilometers and a mass more than twice that of all the other planets combined, Jupiter looms as a great banded sphere of tan, orange, and white. Composed mostly of hydrogen and helium gas, it is often likened to a failed star. It would have needed to be about 80 times more massive to ignite fusion in its core. Instead, Jupiter shines not by its own light, but by reflecting the sun's, and by emitting a bit of heat it retains from its formation. When you gaze at Jupiter through a telescope, you see not a solid surface, but the tops of its cloud decks, organized into parallel bands that wrap around the planet's fast rotating body. Jupiter spins on its axis in just under 10 hours, an incredibly fast rotation for such a huge planet. This rapid spin flattens Jupiter slightly and drives strong jet streams that separate its cloud bands. The most famous feature in Jupiter's atmosphere is the Great Red Spot, a titanic storm roughly 1.3 times the width of Earth that has raged for centuries like a cosmic hurricane. Its brick red clouds swirl counterclockwise in Jupiter's southern hemisphere. Though it has been shrinking in recent decades, the red spot remains an icon of planetary science, a reminder that weather on other worlds can be on a scale far beyond anything on Earth. Jupiter's entire atmosphere is dynamic. Smaller storms come and go, white ovals and brown barges drift in the cloud lanes, and lightning crackles within towering thunderheads the size of continents. Near the poles, Jupiter's Juno spacecraft has revealed clusters of cyclones arranged in geometric patterns. At the North Pole, a central cyclone is encircled by 8 others like a flower of storms, all enduring and maintaining a surprisingly stable configuration. At the cloud tops, the temperature is around 45 degrees, but it grows hotter and denser as you descend. There is likely no sharp surface where gas turns to liquid. Rather, as pressure increases, hydrogen gas gradually becomes a supercritical fluid, and then a weird metallic form in Jupiter's depths. Beneath the storms, Jupiter hides more wonders. Its immense gravity compresses its interior to extreme pressures. Deep down, the hydrogen is squeezed into a state where it conducts electricity like a metal. This metallic hydrogen region, rotating rapidly, is believed to generate Jupiter's powerful magnetic field, the strongest of any planet, with a magnetosphere that extends millions of kilometers and envelops Jupiter's moons. This magnetic field traps charged particles and produces intense radiation belts. It also powers brilliant auroras at Jupiter's poles, glowing in ultraviolet and infrared, far larger and more energetic than Earth's. The interplay of Io's volcanoes and Jupiter's magnetosphere even creates a permanent flow of electric current between them and fills Jupiter's environment with sulfur and oxygen ions that contribute to auroras and radio bursts. Surrounding Jupiter is a retinue of moons, more than 90 known at last count, ranging from tiny asteroid-like rocks to planet-sized spheres. The four largest, the Galilean moons, were first seen by Galileo in 1610 and remain some of the most remarkable places in the solar system. Closest to Jupiter orbits Io, a tortured volcanic world. Io is the most volcanically active body in the solar system. Its interior flexed and heated by Jupiter's gravity. Its surface is mottled with sulfurous yellows and oranges and dotted with erupting volcanoes that spew fountains of lava and giant plumes of sulfurous gas that can rise 300 kilometers high. Next out is Europa, a smooth, icy moon slightly smaller than Earth's moon. Europa's surface is crisscrossed with reddish-brown cracks and ridges over a bright white shell of water ice. Almost no craters mar Europa. It's young and active. Beneath that ice, scientists are confident lies a global ocean of liquid water, kept fluid by tidal heating. Europa's hidden ocean, perhaps 100 kilometers deep under an ice crust a few to 30 kilometers thick, makes it one of the prime candidates in the search for extraterrestrial life. Beyond Europa comes Ganymede, the largest moon in the solar system. Ganymede is a frozen world with a mix of old, dark, cratered regions and somewhat younger, lighter grooved terrain from past tectonic activity. It even has its own internally generated magnetic field, the only moon known to have one, hinting at a molten iron core within. And then Callisto, the outermost Galilean moon, an ancient cratered ball of ice and rock that appears to have changed little in 4 billion years. Callisto's surface is saturated with impact scars, a record of the early solar system's heavy bombardment. While not as flashy as Io or Europa, even quiet Callisto might harbor a subsurface ocean, and it has a composition like a primordial mix of rock and ice, a relic of the solar nebula. Each of these moons could warrant chapters of their own, and indeed they will come up again when we talk about habitability and exploration. For now, they underscore Jupiter's role as a mini solar system, a master planet with its own complex gravitational web, shaping the lives of its moons. Jupiter also sports a barely visible ring system, thin bands of dust encircling the planet above its cloud tops. Unlike Saturn's bright icy rings, Jupiter's rings are tenuous and were discovered only when Voyager 1 flew through Jupiter's shadow and saw them glint. The dust likely comes from meteoroid impacts on small inner moons. The rings remind us that all giant planets have rings of one form or another, a natural consequence of having many orbiting bodies and frequent collisions or ice eruptions to supply ring material. Now we move one step farther out to Saturn, the sixth planet from the Sun, often considered the most beautiful. Saturn is a gas giant like Jupiter, but slightly smaller and significantly less massive. In fact, Saturn has the lowest density of any planet, less than water, meaning if you could find a bathtub big enough, Saturn would float. Visually, Saturn is stunning for one reason above all: its rings. Saturn's rings form a broad, flat disk encircling the planet's equator, composed of countless icy particles ranging in size from dust grains to boulders. They sparkle in the sunlight and are divided into several major rings separated by gaps. From Earth, even a small telescope shows Saturn's rings as a separate structure. Up close, they resolve into myriad ringlets, ripples, and braids sculpted by gravitational interactions with Saturn's moons. The rings are extremely thin, only tens of meters thick in most places, despite spanning over 250,000 kilometers in diameter. They are likely relatively young and are slowly evolving. Saturn's gravity is pulling ring material inward, which means the rings may gradually thin out over tens of millions of years. For now, however, they are a breathtaking demonstration of cosmic geometry and physics.
a disk of ice grains tracing the invisible lines of Saturn's gravity and rotational balance. Saturn itself, beneath the rings, is often seen as a pale golden globe banded by subtle belts and zones like Jupiter's, but far more muted in color. Its upper clouds are composed of ammonia crystals. Deeper down likely lie clouds of ammonium hydrosulfide and water, but these are hidden beneath hazes. Saturn's atmosphere is colder than Jupiter's, and its weather, while not as vividly colored, can still be violent. Roughly once per Saturnian year, Saturn experiences a great white spot, an enormous storm that erupts and encircles the planet. One such storm was observed by Cassini in 2011. It began as a brilliant white cloud in the northern mid-latitudes and spread into a band that wrapped around Saturn, accompanied by lightning and turbulent swirls the size of Earth, before dissipating. Saturn also exhibits a bizarre phenomenon at its north pole, a long-lived hexagonal jet stream pattern, first noticed by Voyager and later seen in detail by Cassini. This six-sided wave, like flow of clouds, each side longer than Earth's diameter, rotates as a unit around the pole. At the center of the hexagon sits a whirling hurricane, like vortex with an eye several thousand kilometers across. Why Saturn's atmosphere naturally forms a hexagon is still debated. Likely it's a result of a standing wave in the fluid dynamics of its atmosphere at that latitude. Like Jupiter, Saturn radiates more heat than it receives from the Sun, though the mechanism is different. Saturn appears to be undergoing helium rain as the planet cools. Helium condenses out of the hydrogen, helium mixture in the upper layers and falls inward, releasing gravitational energy as heat. This helps drive Saturn's weather from below. Saturn's magnetic field is strong. Uniquely, Saturn's magnetic field is almost perfectly aligned with its rotation axis, a fact that challenges dynamo theories. Nevertheless, Saturn has bright auroras observed at ultraviolet wavelengths, and its strong field traps some radiation. Saturn's family of moons is rich and varied, more than 80 known moons. The largest, Titan, is one of the most intriguing objects in the solar system. Titan is bigger than Mercury and enveloped in a thick orange haze of atmosphere. In fact, Titan is the second largest moon and the only moon with a substantial atmosphere, even denser at the surface than Earth's, composed mainly of nitrogen with a few percent methane. For a long time, that smog hid Titan's surface completely. But the Cassini mission's radar and the Huygens lander unveiled a world surprisingly Earth-like in some ways. Titan has rivers, lakes and rain, but of liquid methane and ethane instead of water. At Titan's frigid surface temperature of 179 degrees, water is as hard as rock, and hydrocarbons take the role of the water cycle. Dark methane seas dot Titan's polar regions, complete with shoreline features, islands, and possibly waves. There are branching river channels carved by methane rain flowing into valley networks, and extensive equatorial dune fields made of exotic organic sand. Standing on Titan, you would see an orange-colored sky and a dim sun. The air pressure is about 1.5 times Earth's. You could almost fly by flapping wings strapped to your arms, given Titan's dense air and low gravity. It is an alien yet eerily familiar landscape. In fact, perhaps the most Earth-like place in the solar system, aside from Earth itself, albeit at cryogenic temperature and with a completely different chemistry. Titan likely has a subsurface water ocean as well, beneath the ice crust, making it a double world of interest. A possible haven for some form of life in the warm water below, and a laboratory for prebiotic chemistry in the organic, rich surface environment. Another of Saturn's moons has seized our attention, Enceladus, a small ice moon only about 500 kilometers across. Enceladus looks like a shiny white snowball, reflecting almost all sunlight. For years, its smooth, bright surface hinted something was renewing it. The Cassini spacecraft confirmed that in spectacular fashion. It discovered active water geysers erupting from Enceladus's south pole. Dozens of icy jets spray water vapor and tiny ice particles continuously into space, feeding Saturn's faint E-ring and indicating a subsurface ocean of liquid water beneath Enceladus's fractured crust. Cassini even flew through the plumes and detected salts, organics, and tiny grains of silica. In other words, Enceladus has nearly all the ingredients for life: water, heat, and organic molecules. And it's ejecting them into space, begging for further exploration. The surface around the South Pole has tiger-stripe fissures that are warm and flexing with tidal pulls from Saturn, essentially cryovolcanic vents. This little moon, with a global ocean about 30 kilometers distance below an ice shell some 20 kilometers thick, has become one of the prime targets in the search for extraterrestrial life. Saturn's other moons offer delights as well. Iapetus, half of its surface bright as snow and the other half dark as coal, with a unique equatorial ridge that makes it look like a walnut. Rhea, Tethys, and Dione, medium-sized moons, heavily cratered and cut by ancient canyons. Dione might hide a subsurface ocean too. Mimas, with its giant crater, Herschel giving it a Death Star appearance. Phoebe, a retrograde irregular moon perhaps captured from the outer solar system, rich in primitive material. Each moon tells a different chapter of Saturn's story, from formation to capture to geologic evolution. Yet, through it all, Saturn's majestic rings cast their shimmering veil, illuminating the night sides of moons and casting shadows that stripe Saturn's own cloud tops in eclipse season. Beyond Saturn, the sunlight becomes faint. We reach the ice giants, Uranus and Neptune, the seventh and eighth planets. They are called ice giants, not because they are made of solid ice, but because in addition to hydrogen and helium, they contain a higher proportion of ices, water, ammonia, methane, in a hot, slushy, fluid state inside. Uranus orbits about 2.9 billion kilometers from the Sun, taking 84 years to complete one orbit. It's a pale blue-green orb, about 4 times Earth's diameter, and notably tilted over on its side. Uranus's axial tilt is 98 degrees, meaning it practically rolls around the Sun like a ball. This bizarre orientation is likely due to a colossal collision with a protoplanet long ago. The consequence is extreme seasons. Each pole gets 42 years of continuous sunlight, then 42 years of darkness. When Voyager 2 flew by in 1986, it was southern summer, and Uranus's south pole faced the Sun almost directly. Voyager saw a virtually featureless sphere, a smooth cyan disk with only the faintest hints of cloud, bands or spots. Uranus looked like a painted marble, leading many to call it bland. But as Uranus approached its equinox in 2007, Earth-based telescopes and Hubble started seeing signs of weather: bright white cloud caps, dark spots, and streaky clouds. Uranus, it turns out, has a dynamic atmosphere that awakens when the Sun's heating is distributed more evenly. During the 2010s, astronomers observed some storms with ferocity comparable to Neptune's, including one huge storm in 2014 that was surprising given how far from the Sun Uranus is. Most of the time, though, Uranus is tranquil looking, with gentle banding visible in enhanced images, and a serene aquamarine hue due to methane in its atmosphere, absorbing red light and reflecting blue, green. At cloud tops, Uranus is a frigid 215 degrees Celsius. Uranus also comes with rings and moons. It has a set of thin, dark rings made of radiation, darkened ice, and dust. They are narrow, kept in line by shepherd moons, and not nearly as showy as Saturn's, but they form a delicate series of hoops around the sideways planet. Uranus's moons include Titania, Oberon, Ariel, Umbriel, and Miranda. They are icy, cratered worlds, a few showing evidence of past internal activity. Miranda, for instance, displays one of the strangest surfaces in the solar system: patchwork regions of ridges and valleys next to older cratered terrain, and a cliff estimated at 20 kilometers high. a fall from which would take 15 minutes in Miranda's weak gravity. It's as if Miranda was shattered and reassembled or underwent partial melting that froze in bizarre patterns. The larger moons have lesser quirks. Ariel has relatively few craters and signs of youthful resurfacing. Titania has giant canyons. Uranus's moons, like the planet, roll on their sides as they orbit which means, at solstices, one hemisphere of each moon is in continuous sunlight and the other in darkness. What seasonal effects that might cause on those frigid surfaces, we don't really know yet. Neptune, the eighth planet, orbits about 4.5 billion kilometers from the Sun, taking 165 years for one circuit. It's very similar to Uranus in size and composition, but Neptune is notably more active and more intense in color, a deep azure blue. Discovered in 1846 by mathematical prediction, Neptune was visited by Voyager 2 in 1989. Voyager 2 found a dynamic atmosphere, a great dark spot in the southern hemisphere and bright white clouds zipping around. Neptune's winds are the fastest in the solar system, up to 2,100 km/h, especially around those dark oval storms. The great dark spot seen in 1989 was a large high-pressure system exposing darker gases below, roughly the size of Earth, and it vanished a few years later. But other dark spots have since appeared and faded on Neptune. Unlike Jupiter's huge stable spot, Neptune's seem to be shorter, lived storms that come and go every decade or so. Neptune's upper atmosphere is about 200 degrees. Intriguingly, Neptune, like Jupiter and Saturn, radiates about 2.6 times more heat than it gets from the Sun, likely due to residual heat from formation. This internal energy might help drive the vigorous weather we see. Neptune's seasons last over 40 years. We haven't observed a full Neptunian season change yet, but in the decades since 1989 to the 2020s, we've seen some puzzling climate changes. The global temperature in Neptune's stratosphere actually dropped by about 7 degrees Celsius from 2003 to 2018. Then the South Pole suddenly warmed by 11 degrees from 2018 to 2020. It's a reminder that these far-off atmospheres can have variability we don't fully grasp yet. Neptune, too, has rings and moons. It sports faint rings with clumpy arcs. The outer Adam's ring has segments named Liberty, Equality, and Fraternity, where dust is clustered, for reasons initially mysterious until moonlets were found that shepherd those arcs. And Neptune's moon's number 14 at last count. The standout is Triton, Neptune's largest moon, which orbits backward relative to Neptune's rotation. Triton is a captured Kuiper belt object, likely snared by Neptune's gravity long ago. Triton is an ice world almost as big as our moon, with a young surface of frozen nitrogen, water ice, and weird cantaloupe terrain, and it is geologically active. Voyager 2 saw geysers on Triton, dark plumes of nitrogen gas and dust spraying up from the surface, carried by winds before falling. These are essentially cryovolcanoes driven by seasonal heating of Triton's south polar cap. Triton's thin atmosphere is about 1/70,000th Earth's pressure, but enough to have winds that bent those geyser plumes. Triton is extremely cold, yet it still has this slight atmosphere and active geysers, an astounding find. Triton likely has a subsurface ocean as well, kept liquid by residual internal heat or past tidal heating. Because of its retrograde orbit, Triton is slowly spiraling inward toward Neptune. Billions of years from now, it may either break apart into a spectacular ring or crash into Neptune. Neptune's other moons are much smaller and ice, rocky. Nereid has an extremely elongated orbit. Proteus is the second, largest, but still irregularly shaped. It's as large as an object can get without its gravity crushing it into a sphere. Proteus, dark and heavily cratered, might have avoided melting into a sphere by forming late, after the solar system calmed down. Tiny Hydra and Naiad and others zip around Neptune in closer orbits, some in complex resonant dances. Neptune's moon system likely lost whatever original satellites it had during Triton's capture. What we see now are either captured asteroids, comets, or fragments of an ancient moon system reassembled in new orbits. Thus, the outer solar system presents grandeur quite different from the inner. Here we have giant globes of gas and ice, lacking solid surfaces, but adorned with storms larger than Earth and delicate rings. We have an array of moons that are worlds in their own right, some sterile and cratered, others with subsurface oceans or thick atmospheres or erupting geysers. The giant planets act as architects and guardians of the solar system. Their gravity shaped the orbits of countless smaller bodies and may have steered water, rich comets toward the inner planets, possibly delivering Earth's oceans. Jupiter, especially, has shielded the inner solar system at times by vacuuming up comets, though it can also fling asteroids our way if they get too close. The giants likely migrated early on, scattering the debris disk and causing the late heavy bombardment that peppered the inner worlds with craters, and perhaps ejecting leftover planetesimals to form the distant Oort cloud of comets. As we leave Neptune behind, we pass into the realm of icy debris, the Kuiper Belt and beyond, where the sun's influence wanes. Yet even here we find worlds of consequence, the dwarf planets, which challenge how we define planethood and carry clues to the solar system's origin. Dwarf planets, worlds at the edge, and the definition of planethood. Far beyond Neptune's orbit, the solar system continues into a vast realm of icy bodies. Here, in the dim frontier, lies the Kuiper Belt, a broad ring of frozen remnants from the solar system's formation. Among these are several worlds large enough to be round, worlds that in another context might have been called planets. In fact, one of them was long honored as the 9th planet, Pluto. Today, we classify Pluto and similar bodies as dwarf planets, a category born from the realization that our cosmic neighborhood has more planets than we once thought, and that not all planets are equal in their orbital status. These distant dwarfs are small in size but rich in diversity, and they have forced us to confront the question, what does it truly mean to be a planet? Let us begin with Pluto, the iconic dwarf planet and former 9th planet. Discovered in 1930, Pluto orbits roughly 5.9 billion kilometers from the Sun on average, on a path that is highly inclined and elliptical. For 76 years, it was counted as the outermost planet, depicted as an icy oddball, until the early 21st century brought a paradigm shift. Pluto is about 2,377 kilometers in diameter, less than 20% of Earth's diameter, smaller than our moon. But what it lacks in size, Pluto makes up for in personality. In 2015, NASA's New Horizons spacecraft flew past Pluto and revealed an astonishingly complex world. Far from a simple cratered ice ball, Pluto displays a mosaic of terrains. Towering water, ice mountains rising 4,006 kilometers high, vast smooth plains of nitrogen ice with no craters, and dark reddish regions rich in organic molecules processed by sunlight. The most famous feature is Tombor Regio, nicknamed the heart of Pluto, a bright, heart-shaped area dominating one hemisphere. The left lobe of this heart, Sputnik Planitia, is a 1,000 km wide basin filled with nitrogen, carbon monoxide, and methane ices. This frozen plain is segmented into polygonal cells, evidence of convection. Pluto's interior heat causes the nitrogen ice to slowly overturn like a lava lamp, erasing craters and renewing the surface. It's a bit mind-boggling. Here is a tiny world at the solar system's edge, with active geology powered perhaps by the slow cooling of an internal ocean, or by exotic forms of heat transfer in the ice. Pluto's thin atmosphere is another surprise. When near perihelion, its surface ices sublimate, forming a tenuous atmosphere of nitrogen with a touch of methane. This atmosphere is about 100,000 times thinner than Earth's, but enough to form layers of delicate blue haze, as imaged by New Horizons when it looked back at Pluto, eclipsing the distant Sun. In Pluto's sky, the Sun is just a brilliant star, but it still drives a faint weather cycle. As Pluto recedes from the Sun, its atmosphere can partially freeze out onto the surface. New Horizons saw that Pluto's skies are layered with haze up to 200 kilometers altitude, and that the atmosphere is slowly escaping to space, forming a tail like a comet's. Standing on Pluto, you'd see a dim daylight with a charcoal-colored landscape, low gravity, and if you looked up, a thin bluish glow around the horizon from the atmospheric haze. Pluto doesn't wander alone. It has a system of 5 moons. The largest, Charon, is so big that Pluto and Charon Co. orbit each other around a point in space between them. Charon itself is a fascinating world. New Horizons showed it has a rugged surface with a massive equatorial canyon system far longer and deeper than the Grand Canyon, and a strangely bi-colored complexion. The northern polar region of Charon is reddish, likely stained by gases that escaped Pluto and froze onto Charon, then were altered by solar radiation into reddish tholins. The mutual orbit of Pluto and Charon is tidally locked. Each keeps the same face toward the other, waltzing through space as an inseparable pair. Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, are much tinier and irregularly shaped, probably captured or coalesced debris from the giant impact that created the Pluto-Charon system billions of years ago. Moving outward, we find Eris, the troublemaker that precipitated Pluto's demotion. Eris was discovered in 2005 by a team led by Mike Brown. It's an object currently slightly smaller in diameter than Pluto, but more massive by about 25%. Eris orbits the Sun on a highly eccentric path. When found, Eris was hailed in the media as the 10th planet, but its existence underscored that Pluto was not unique. Astronomers suspected many Pluto-sized objects awaited discovery. Eris was named after the Greek goddess of discord, fitting for the chaos it introduced into our understanding. It has one known moon, Dysnomia. Eris's surface is extremely bright. Its great distance means Eris is in deep freeze. If it comes closer, it might develop a thin atmosphere like Pluto's that refreezes when far out. Eris's discovery forced the IAU to formalize the definition of planet, and under that definition, Eris joined Pluto as a dwarf planet. But in terms of geology and interest, Eris is very much a planet, like world, simply one of a vast collection in the Kuiper belt. Besides Pluto and Eris, the IAU has so far recognized 3 other dwarf planets: Ceres, Haumea, and Makemake. Ceres is unique as the only dwarf planet located in the inner solar system, residing in the asteroid belt between Mars and Jupiter. In fact, Ceres was the first dwarf planet discovered and initially considered a planet until many more asteroids were found. Ceres is about 940 kilometers in diameter, roughly the size of Texas, and contains about a third of the mass of the entire asteroid belt. NASA's Dawn orbiter visited Ceres in 2015 and unveiled a cratered world that, while much smaller than Pluto or Eris, still shows signs of internal complexity. Most famously, Dawn spotted mysterious bright spots on Ceres, particularly in the crater Ocata. These bright patches turned out to be deposits of salts left behind by briny water that erupted or seeped to the surface, essentially cryovolcanic salt flats. This indicates that Ceres, even at its modest size, had a subsurface reservoir of salty water or mud that occasionally breaches the surface as a kind of ice volcano. One such cryovolcano on Ceres is Ahuna Mons, a solitary mountain likely formed by the extrusion of viscous, icy material that then hardened. Ceres likely differentiated into a rocky core and icy mantle. It may even hold a remnant subsurface ocean or pockets of liquid. Though cold and airless, Ceres surprises us by being a kind of geological bridge between the rocky inner worlds and the icy outer worlds. Back to the Kuiper belt, Makemake is another dwarf planet, slightly smaller than Pluto. Discovered in 2005, Makemake orbits at about 45 AU on a mildly tilted orbit. It has a very high reflectivity as well, with a surface of methane and ethane ices that give it a red-brown color. For a long time, Makemake was thought moonless, but in 2016, a tiny moon was found in Hubble images. Knowing its moon will allow us to determine Makemake's mass and density. Makemake has no known atmosphere, and its average surface temperature is around 240 degrees Celsius. Then there is Haumea, one of the strangest known dwarf planets. Discovered in 2004 and officially named in 2008 after the Hawaiian goddess of childbirth, Haumea is not spherical but rather ellipsoidal due to its incredibly rapid rotation. A day on Haumea is just under 4 hours. This fast spin elongated Haumea into a rugby ball shape. It's as if someone grabbed a ball of taffy and whirled it around. The centripetal force stretched it out. Haumea is also notable for its composition. It's largely water ice with a denser core, suggesting it might be the fragment of a larger body that collided and spun up. Supporting that, Haumea has 2 moons and is associated with a swarm of smaller Kuiper belt objects that share similar orbits and water-ice spectra, likely pieces of Haumea's shattered past self. In 2017, observers caught Haumea eclipsing a star and discovered it even has a ring, a 70-km wide ring of particles around its equator, likely in the plane of its fast rotation. Haumea's existence stretched our idea of a planet, showing that something can be round-ish and orbiting the sun, yet far from symmetric or solitary. Beyond these, dozens of other objects around the size threshold for dwarf planet likely exist. Quaoar has a moon and possibly a ring of its own. Sedna lurks on an 11,000-year orbit that takes it out to nearly 1,000 AU, possibly the first known member of the inner Oort cloud. The more we look, the more we find a continuum of worlds bridging planets and comets. The dwarf planets collectively highlight the continuum of planetary sizes and the gradations in the solar system's architecture. They forced the question, where do we draw the line between planet and smaller bodies? The 2006 IAU definition drew that line based on orbital dominance. By that rule, Pluto, Eris, Haumea, Makemake, and Ceres were reclassified because they share their space with many peers, but that definition remains debated. Some planetary scientists prefer a geophysical definition. If it's round by self-gravity, call it a planet, which would make dwarf planets planet in a broader sense. Others note that even Earth hasn't entirely cleared its orbit, but Earth so overwhelmingly outweighs them that the spirit of the definition holds. The public often still refers to Pluto as a planet out of affection. In truth, terms like planet are human categories we impose on nature's spectrum. Whether we call Pluto a planet or not doesn't change Pluto itself, with its glaciers of nitrogen, atmosphere that snows out, and potential subsurface ocean. Pluto defies any notion of being a static asteroid. We've learned that these so-called dwarfs can be just as complex and geologically active as the big planets. They are worlds by any meaningful measure. The classification is mainly about how they fit into the solar system's structure. Pluto hasn't cleared its orbit because it lives in a bustling disk of other icy bodies. That tells us about where and how it formed, but it doesn't diminish its status as a fascinating world. Indeed, studying dwarf planets like Pluto and Ceres has yielded huge insights. Ceres taught us that even small bodies can differentiate and possibly harbor liquid water or mud under the surface. Pluto showed that even in the far frozen reaches, geology goes on. Exotic ices can flow and convect like glaciers, and cryovolcanoes can build mountains. These bodies are time capsules from the solar system's formation and laboratories for processes at the extremes. They and their ilk likely delivered volatiles to the larger planets. And when we consider planets around other stars, many might be more akin to these intermediate worlds than to the 8 major planets we started out with. Having completed our grand tour of the solar system, from the sun, scorched rocks, to the gas leviathans and distant ice dwarfs, we can step back and summarize. Our solar system contains a family of worlds with a common origin, but wildly divergent paths. Some went dry and airless, others drowned in thick atmospheres. Some stayed warm inside, churning and resurfacing, others went cold and quiet. And around at least one modest star out of billions, one small rocky planet found a perfect balance and became alive. With this perspective, we now venture beyond the solar system to the planets that orbit distant suns. Here, we will apply what we've learned to understand how we detect these alien worlds, what types we've discovered, and what that means for the potential for life in the cosmos. Beyond our solar system, the exoplanet revolution. For thousands of years, humans wondered if the stars in the night sky had their own planets. In the last few decades, we found the answer, a resounding yes. We are living through a revolution in which exoplanets, planets around other stars, have gone from speculation to a catalogue of thousands. This discovery has expanded our concept of what a planet can be and placed our solar system in a galactic context. The first discoveries were surprising. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the first confirmed exoplanets, and they were orbiting a pulsar. These were likely bizarre worlds that survived a supernova or coalesced from its aftermath. Not at all what we expected for the first planets beyond our solar system. Then, in 1995, Michel Mayor and Didier Queloz discovered the first exoplanet around a sun-like star, 51 Pegasi b, a planet at least half the mass of Jupiter, but orbiting so close to its star that its year is only about 4 days. This was a hot Jupiter, a kind of planet unknown in our solar system. It forced us to realize that planetary systems can be very different from ours. Since then, a torrent of discoveries has followed. Astronomers detect exoplanets mainly by two methods: the radial velocity method, which measures the star's subtle wobble due to an orbiting planet's gravity, and the transit method, which measures the slight dimming of a star when a planet crosses in front of it. The Kepler Space Telescope stared at 150,000 stars and measured their brightness precisely, catching thousands of tiny dips that revealed over 2,600 confirmed exoplanets. These planets range from larger than Jupiter gas giants to smaller than Earth worlds. We learned that super-Earths and mini-Neptunes are extremely common, yet our solar system has none of those, implying our setup might be somewhat unusual. We found hot Jupiters, gas giants hugging their stars in scorchingly tight orbits, and hot Neptunes and warm Saturns, and more. We found multi-planet systems packed in close to their stars, some with planets in orbital resonances. We found circumbinary planets, planets orbiting two stars. We found free, floating planets by gravitational microlensing, rogue worlds that drift through the galaxy untethered to any star. And we found planets in the habitable zones of their stars, at distances where, if conditions are right, liquid water could exist on a rocky surface. One of the most exciting sets of discoveries was the TRAPPIST system. 7 Earth-sized planets orbiting a dim red dwarf star only 39 light-years away. 3 of these lie in the star's habitable zone. They are all tidally locked and crammed in a space that would fit well within Mercury's orbit. This system provides a tantalizing example of a very different kind of solar system architecture, one where a tiny star can have a retinue of Earth-size worlds potentially capable of retaining atmospheres. What are their surfaces like? Could any have water or life? Future telescopes like the James Webb Space Telescope are actually beginning to probe their atmospheres by analyzing starlight that filters through during transits. Exoplanets have shown us an astounding diversity of types. Hot Jupiters, gas giants orbiting extremely close to their stars. These have atmospheric temperatures of 1,000 pounds and 2,500 excites or more. Their atmospheres are puffed up by heat. Some are losing gas under the stellar radiation. They challenged our formation models. How did such big planets get there? We think they formed farther out and then migrated inward due to interactions with the protoplanetary disk or other planets. They taught us that migration can be a common process. Super-Earths. Planets a bit larger in radius or mass than Earth. Some may be rocky, others may have thick atmospheres. They might actually span a spectrum from big rocky planets to small gas planets. Not having one in our system means we had a gap in our understanding. Now we see they might be one of the most common types in the galaxy. A super-Earth might have higher gravity and retain a thick atmosphere or oceans for billions of years. Could they be even more clement for life than Earth? Or could they all turn into gas dwarfs with puffy atmospheres that make them uninhabitable? We're trying to find out by measuring their densities. Some super-Earths like 55 Cancri E are very dense, whereas others like Kepler 38d appear to have low density. Ice giants and sub-Neptunes. Many systems have planets in the 2 through 4 Earth radii range, akin to scaled down versions of Neptune and Uranus. These might have thick hydrogen, helium atmospheres on a rocky/icy core. Some could be more water-rich. The line between super-Earth and sub-Neptune might be around 1.6,001 Earth radii. Intriguingly, Kepler data showed a dip in planet frequency around that size, suggesting many planets either have significant gas envelopes or have almost none. This phenomenon, the radius gap, likely reflects how planets either stop growing early and stay rocky or accumulate enough gas to puff up. The borderline worlds might have lost some atmosphere due to stellar radiation, ending up as rocky cores. Gas giants. Plenty of Jupiter, like or Saturn, like exoplanets have been found at various distances, some close, some at Earth, like distances, some far out. A few even orbit at Jupiter, like distances from Sun, like stars, implying their systems might have distant architectures vaguely resembling ours. We found giants in eccentric orbits. Some gas giants orbit binary star systems. We've even directly imaged a few young gas giants at wide separations. Rogue planets. Gravitational microlensing surveys have hinted that there may be numerous free-floating planets, perhaps ejected from forming systems or formed in isolation. Some estimates suggested they could be as numerous as stars or more, though recent data suggests not that common for Jupiter mass ones. Still, it implies planet formation can be a turbulent process, with some worlds flung into the galaxy to wander alone. These would have no sunlight, just faint glow from leftover heat or radioactivity. A larger rogue could retain a thick atmosphere and maybe an internal ocean kept liquid by radiogenic heat or tidal heating from a prior moon, but life on such worlds would be a stretch. Exotic worlds. Some planets are simply weird, like lava worlds such as Corot 7b or Kepler 10b. Rocky planets so close to their stars that their surfaces are likely molten on the dayside, with rock vapor atmospheres and mineral clouds that rain pebbles. Or ocean worlds that might be nearly all water by mass, essentially giant versions of Europa or Enceladus that grew larger. There's the idea of carbon planets around stars with different compositions, perhaps worlds where graphite and diamonds are abundant, or surfaces of carbide rock under tar, like skies. There are also puffy planets, gas giants with anomalously large radii for their mass, like WASP 17b, which is about half Jupiter's mass, but 1.7 times its size, and planets orbiting pulsars, or extremely metal, poor stars, or white dwarfs, each situation leading to unusual characteristics. When we compare these exoplanets to our solar system, we see that our system might not be typical in some respects. The absence of a super-Earth in our solar system is a puzzle. Perhaps Jupiter's formation prevented one from coalescing by scattering material. The lack of hot Jupiters in our system is a blessing for us. It appears that giant planets that migrate can disrupt inner systems heavily, whereas ones that stay put allow inner rocky planets to remain. Our relatively circular orbits and spaced-out configuration might not be the most common outcome. Many stars have multiple super-Earths in orbits closer than Mercury's, for example. Yet, among Sun-like stars specifically, some analyses suggest systems with a giant planet at Jupiter, like distance and small inner rocky planets, could be not extremely rare either. We're still trying to figure out how special our arrangement is. The significance of discovering exoplanets is profound. We now know that planet formation is a natural part of star formation. Planets are everywhere. The galaxy likely holds tens of billions of potentially habitable rocky worlds. We've taken the concept of planet from 5 wanderers in the sky to a cosmic norm, and each type of planet we find tests our theories. How do hot Jupiters form? Likely through disk migration or interactions. Why are super-Earths so common? Perhaps many systems form multiple mid-sized cores, which either become super-Earths or mini Neptunes, depending on how much gas they capture and how fast they migrate. What about Earth-like planets? Statistical studies from Kepler suggest perhaps 20–25% of Sun-like stars have an Earth-size planet in the habitable zone. Around red dwarfs, potentially an even larger fraction have Earth-size planets in the habitable zone, as seen with TRAPPIST and others. However, red dwarfs are volatile. Their flares and long-lived activity might strip or sterilize those planets' atmospheres. The search is now shifting from finding exoplanets to characterizing them, measuring their masses and radii, detecting their atmospheres via spectroscopy, and even directly imaging some. We have detected atmospheric constituents on some exoplanets, sodium in hot Jupiter atmospheres, water vapor on some, even hints of things like titanium oxide, or possibly clouds of silicates or iron. In 2019, water vapor was detected in the atmosphere of a sub, Neptune, in its star's habitable zone, raising interest. The ultimate goal is to detect biosignatures, signs of life, in an exoplanet's atmosphere, such as oxygen or methane out of equilibrium, or other peculiar combinations that strongly suggest biology. That will require the next generation of telescopes and perhaps specialized space observatories with coronagraphs or star shades to directly see Earth, like planets next to their bright stars. The types of exoplanets we've discovered inform our quest for life. We've learned that terrestrial planets often come in families. A star might have several, some perhaps larger or smaller than Earth. We've seen that habitable zones around red dwarfs can host multiple tidally locked Earth-size worlds. Whether those can support life is an open question. Tidal locking means one side is always hot, the other cold. But if they have atmospheres or oceans, they could redistribute heat. We also consider how giant planets in a system might affect habitability. A Jupiter analog could help by diverting comets or hinder by destabilizing orbits. Our solar system's giant planets likely had a hand in delivering water, and also in preventing too many super-Earths from forming in the inner regions. In the context of habitability, the solar system offers 3 main candidates for life as we know it: Earth, Mars, and ocean moons. But none besides Earth have confirmed life. So as we look outward, we refine what conditions might be needed. Liquid water, certainly, is high on the list. A source of energy is needed. A stable environment over some billions of years might be necessary for complex life. Planets in the habitable zone of Sun, like stars, might be best situated for that. Red dwarf habitable zone planets get a lot of flares, especially in youth. Could life survive that? Possibly, if under ocean or ground, or protected by a magnetic field and thick atmosphere. We remain cautious but hopeful. The future exploration of exoplanets is accelerating. The James Webb Space Telescope is already peering into some transiting planets' atmospheres with unprecedented detail. Upcoming missions like the Nancy Grace Roman Space Telescope will use microlensing to find rogue planets and cold planets further from stars, and test technologies for direct imaging. Further down the line, proposals for missions like LUVOIR or HABEX specifically aim to directly image Earth like planets around Sun, like stars, and search their spectra for biosignatures. On the ground, extremely large telescopes coming online in the late 2020s will be able to probe smaller exoplanets and perhaps take crude spectra of super-Earth atmospheres. It's conceivable that in the coming decades we might identify a planet where life could exist, or even find hints that it does exist, such as an atmosphere out of chemical equilibrium, strongly suggestive of biological activity. As our gaze extends to the stars, we carry the lessons of our solar system with us. We now know Earth is not alone as a potentially habitable world. There may be billions of Earths in our galaxy, but we also know habitability is fragile. Climate catastrophes like what befell Venus and Mars remind us that a planet's fate can change drastically. Earth has been lucky, but we must keep it that way. Life among the stars, the quest for habitability. When we talk about habitability, we usually mean conditions suitable for liquid water and life as we know it. From our study of planets, we've identified key factors. Distance from star. The concept of the habitable zone is crucial. Not too hot, not too cold for liquid water on the surface. For our Sun, that roughly spans from just beyond Venus's orbit to just beyond Mars's. For smaller, cooler stars, the habitable zone is much closer in. For bigger, hotter stars, it's farther out, but those stars live shorter lives. Atmosphere. A planet needs an atmosphere thick enough to create pressure for liquid water and to circulate heat, but not so thick as to induce a runaway greenhouse. Too thin, and water either freezes or boils away. The composition matters too. CO2 provides warmth, but too much can cook a planet. Some gases can be toxic to life. On Earth, life itself altered the atmosphere, creating the oxygen we breathe, which in turn allowed complex life. Magnetic field. As we discussed, a magnetic field can protect a planet's atmosphere from stellar winds. Earth's field likely helped us maintain our water and air over geologic time. Mars lost its field early, and then its atmosphere eroded away largely. Venus lacks a field, but its atmosphere is so thick that even with losses, it remains dense. Around active stars, a magnetic field could be even more critical to buffer the planet from high-energy radiation and flares. Internal heat and geology. Plate tectonics appears to help regulate climate via the carbon cycle on Earth. Volcanism also releases trapped gases and replenishes the atmosphere. A geologically dead planet might end up like the Moon. No atmosphere, cold interior, and static surface, not hospitable. Mars's waning volcanism might have doomed its climate. Venus's rampant volcanism may have contributed to its runaway greenhouse by belching massive CO2. A balance of geological activity is likely beneficial, enough to drive cycles and field generation, not so much as to create continuous global volcanism that might make a world too volatile for stable ecosystems. Stable climate and star output. A planet needs time for life to evolve. Earth has had liquid water for almost 4 billion years through various climate swings. A star's output can change. Earth's biosphere and geology compensated, keeping the planet habitable. If the changes were more extreme, or Earth's feedbacks weaker, life might have been snuffed out. So habitability is a combination of initial conditions and subsequent luck and balancing feedbacks. When we look at exoplanets, especially those in habitable zones, we assess these factors. Does the planet likely have an atmosphere? What's the star like? We've identified some promising, potentially habitable exoplanets. Proxima Centauri, B. TRAPPIST, E, F, G, as mentioned. Earth-sized, in or near habitable zone around a dim star. Kepler, 452b, around a Sun-like star, often touted as older cousin of Earth, is larger, and the star is 6 billion years old. Interesting if it's rocky, but we're not sure it isn't too massive, having a thick atmosphere. Kepler, 2F and Kepler, 186 if, are smaller planets in their stars' habitable zones, though their stars are a bit cooler than the Sun. Many others have been found by Kepler and TESS, that are unconfirmed or with limited information. Ultimately, detecting life is the holy grail. What might be a sign of life? On Earth, the combination of abundant oxygen and methane is a strong biosignature. Seeing both would raise eyebrows. Also, things like the spectral edge of chlorophyll could be a signature if we ever got a direct color spectrum of an exoplanet's surface. Even seasonal changes in atmospheric composition could hint at biology. It's tricky because we have only one example of life's impact on a planet, Earth, and alien life might produce different gases. Also, non-biological processes can sometimes mimic biosignatures. So context is everything. We'd need to understand the planet's star, history, and environment to interpret signals, while the exoplanet hunt proceeds mostly via remote sensing. In our own solar system, we can go to these worlds to search for life or conditions. Mars is currently being combed by rovers and orbiters. Europa and Enceladus are top targets. Europa Clipper will orbit Jupiter and repeatedly fly by Europa to map its ice and composition, even scouting for plumes to sample for organic molecules. JUICE will explore Jupiter's moons and eventually orbit Ganymede, studying its ocean and magnetic field. For Enceladus, a future mission concept aims to directly sample its geysers for biomolecules and maybe even signs of microbial life. Titan will be visited by Dragonfly, a flying drone like Lander that will hop across Titan's dunescapes to drill into organics and look for prebiotic chemistry or even life's handiwork. Thus, our exploration strategy is twofold. Within our solar system, investigate all potentially habitable niches. Beyond our solar system, improve our telescopes to identify promising Earth, like planets around nearby stars, and eventually directly image them. We stand at a moment in history where we can, for the first time, meaningfully search for life beyond Earth. Not long ago, planets around other stars was still hypothetical. Now it's routine science. The next leap, finding evidence of life's effects on another world, would be profound. It would tell us whether life is a cosmic common occurrence or a rare fluke. Either answer is deeply significant. If common, the universe may be teeming with biology and perhaps intelligence. If rare, then our pale blue dot is an even more precious oasis in a vast, perhaps mostly sterile desert. Future frontiers, exploring new worlds, and the fate of our planetary journey. What does the future hold for planet exploration? Both in continuing to explore our solar system and in reaching for others, the coming decades promise to be exciting. Within the solar system, several ambitious missions are on the horizon or in progress. We mentioned Europa Clipper and Dragonfly. These will illuminate the potential habitability of ocean worlds. Mars exploration continues. After Perseverance collects samples, a multi-part Mars sample return mission by NASA ESA aims to bring those samples to Earth by the mid-2030s, allowing labs on Earth to scrutinize Martian soil for signs of ancient life with far greater precision than any rover could. Plans for human missions to Mars loom on the multi-decade timescale. The 2030s or 2040s may see the first footsteps on Mars, fulfilling a dream long imagined. Humans could conduct science on Mars that robots struggle with, though robots will likely have already answered the life question by then. At Jupiter and Saturn, the next generation might be missions to actually land or sail in the oceans of the moons. A concept being studied is a Europa lander to drill through a thinner part of the ice, or a penetrator that melts its way down. Even more fanciful is a submarine for Titan's methane seas or an Enceladus ice drilling lander. These are technologically challenging, but so was landing humans on the moon. It's a matter of will and priority. There's also renewed interest in Venus. After decades focusing on Mars, NASA and ESA have recently approved missions to Venus in the 2030s, Da Vinci Plus and Veritas. ESA's Envision orbiter is planned as well. These missions will give Venus a fresh look, important for understanding how Earth, like planets, diverge. If Venus was once more temperate, when and how did it turn so hostile? we might find clues of past water or ongoing volcanic gases. Farther out, Uranus and Neptune remain the only major planets not revisited since Voyager. The US Planetary Science Decadal Survey has prioritized a Uranus orbiter and probe mission for the 2030s. This mission would journey for around 15 years to Uranus, deploy an atmospheric entry probe to sample Uranus's air directly, and orbit Uranus for a few years to study its rings, magnetosphere, and moons. Such a mission would be a bonanza of science. Understanding ice giants will fill a gap in our knowledge of planet formation. After Uranus, Neptune is a logical next target, potentially in the 2040s, possibly with a Triton lander or ocean finder included. These missions, though far off, underscore humanity's commitment to exploring all corners of our solar neighborhood. In the realm of exoplanets, as discussed, new space telescopes like JWST are opening windows. JWST has already begun examining atmospheres of some transiting exoplanets and even directly imaged a couple of gas giants. Over its lifetime, it might be able to probe some super-Earth atmospheres around nearer stars for molecules like water or CO2. The Roman telescope will find many cold exoplanets via microlensing and carry a technology demonstrator coronagraph to directly image a handful of known giant exoplanets, sharpening our skills. By the 2030s or 2040s, we hope to launch a large segmented mirror telescope. Such a telescope, armed with a coronagraph or a starshade, could directly see Earth-sized planets around perhaps dozens of nearby sun, like stars, and take spectra of them, searching for biosignature gases. Imagine seeing a pale blue dot in the sky of another star and detecting, say, oxygen, or even a color variation due to continents and oceans. That would be a civilization, changing discovery. We stand perhaps a generation away from that possibility. There are also imaginative projects like Breakthrough Starshot, which envisions sending gram-sized microprobes to Alpha Centauri using powerful laser sails, reaching 20% the speed of light to get there in about 20 years. While highly experimental, if such technology matured, we could potentially have flyby images of planets around the nearest stars within our lifetimes, perhaps revealing continents or clouds on an alien Earth. It sounds like sci-fi, but no more so than Jules Verne's moon rockets did in the 1860s. Human curiosity drives innovation, and the payoff, touching another star system, would be historic. As we explore, we also reflect. All these worlds we've visited in our minds, from Mercury's battered ground to Neptune's windy blues, have taught us about diversity and commonality. Diversity in that each planet is its own world with unique quirks. Commonality in that they are all part of one grand physical system, obeying the same gravity and chemistry, following similar stages of formation and evolution with variations on the theme. We've seen parallels, volcanoes on Earth and Io, sand dunes on Mars and Titan, polar lights on Earth and Jupiter, ice crusts on Europa, and our own Arctic Ocean. We've seen cautionary tales, a planet almost our twin that became a furnace, a small world that lost its shield and dried out. We look back at Earth with new appreciation for its perfectly tuned conditions, not too hot like Venus, not too cold like early Mars, big enough to hold air, spinning fast enough to have a magnetic field, blanketed by life that in turn helps maintain stability. The study of planets has also put us in our place. Copernicus removed Earth from the center. Galileo showed Earth is just one of many bodies. The last century revealed that even the sun is one of billions, and now that planets abound everywhere, our home is just one island in a vast archipelago of worlds. And yet, to us, it's special, the only known cradle of life. As we search for life elsewhere, we can't help but wonder about the rarity or ubiquity of life. Will we find biosignatures on Mars or Enceladus, or an exoplanet? If we do, It means life might sprout wherever conditions allow, implying a living cosmos with many neighbors. If we don't, it could mean life is a freak accident, a cosmic miracle unique to Earth. In that case, the responsibility on us as stewards of the only garden of life increases immeasurably. Either way, studying planets has given us a cosmic perspective. Carl Sagan's famous pale blue dot speech encapsulated it. All of human history played out on a mote of dust suspended in a sunbeam. Every planet we visit reminds us of the fragility of habitability, how thin an atmosphere is, how delicate a balanced climate can be. We see Venus and fear a runaway greenhouse. We see Mars and fear the loss of a magnetic field and atmosphere. We turn those lessons to our own situation, recognizing our planet's climate is not static, that pumping greenhouse gases can push Earth toward a new, possibly unfavorable state. The barren surfaces of Venus and Mars urge us to be careful lest Earth follow their paths in some distant future by our own doing. Planets also teach resilience and change. Earth has gone through mass extinctions and recovered. Life has a tenacity. Who knows, maybe life exists in some form under the ice of Europa or in Titan's chemical stew, very different from Earth's biology. If we find even a second Genesis in our solar system, it means life is a cosmic imperative. If we don't find it nearby, we'll keep looking outward. Ultimately, the exploration of planets is a human story of curiosity, wonder, and reflection. We have gone from gazing at wandering stars to sending robot emissaries across the void to stand on those worlds and report back. With each step, we've been awed. We felt the volcanic heat of Io and shivered in the methane rain of Titan. We marveled at Saturn's rings, countless icy particles orchestrated by gravity into one of nature's most gorgeous sights. We flew through a geyser on Enceladus and tasted primordial water. We watched a sunset on Mars through the eyes of rovers, its sky tinged butterscotch by fine dust. These experiences, albeit through our mechanical proxies, have enriched our soul and expanded our imagination of what worlds are out there. Looking up at the night sky now, we no longer see just pinpoints of light. We see other suns with their own planets, perhaps a giant with storms bigger than Earth, or a warm ocean world enveloped in clouds, or a rocky orb struggling to hold on to an atmosphere. We might even see lights of another civilization, though none have been detected yet. The possibility is there, made real by the sheer number of planets. So we end our journey where we began, under the stars. But now, when we point out the wanderers, our neighboring planets, we do so with understanding and kinship. The word planet means wanderer, but ironically, planets also taught us how connected everything is. Wanderers though they are, they orbit in a family, influencing each other and their star. And we, wanderers ourselves, have begun to venture from our home to visit them, first with our eyes, then with our ships, someday perhaps in person. The story of planets is the story of cosmic islands and the voyages between them. It's a tale of creation, how dust can clump and ignite, and then leave residue that becomes worlds both barren and lush. It's a tale of destruction and renewal, giant impacts that can destroy worlds or birth moons, atmospheres that can collapse or run wild, but also life that can emerge and transform a whole planet. It's a story that forces us to ask, how common is a world like ours? How rare are we? And where do we go from here? In the next decades, we may finally get an answer to, are we alone? By detecting life signs elsewhere. Or we may find that Earth is singular so far. In either case, planet exploration will continue, driven by the deepest human urges to know and to go. Unmanned or manned, we will likely set foot on Mars, dive into the seas of Europa with submersibles, maybe float in the atmosphere of Titan or Venus in balloons. We will refine our techniques to image Earth like exoplanets. Perhaps one day, far in the future, our descendants will build starships to visit neighboring systems, turning those points of light into landscapes beneath their boots. As our perspective broadens, our appreciation of Earth deepens. The pale blue dot that Sagan spoke of is our only home in a vast cosmos, at least for now. The other planets show starkly that Earth's hospitality is unique in our solar system. So exploring other planets is not just about them, but also about us, holding a mirror to Earth. We see what happens when greenhouse gases go unchecked, or when a small planet cools and dries, or how a protective magnetic field can preserve a world. These lessons are invaluable as we manage Earth's future. Finally, there is an almost spiritual aspect. By understanding planets, we come to understand our place in the universe. No longer are we the center, we are part of something vast and magnificent. The diversity of worlds out there suggests that if life could arise here, it could arise elsewhere. And if it hasn't elsewhere, then we carry an enormous responsibility as the sole known bearers of consciousness to care for our oasis and perhaps spread life beyond it. We began this journey with the ancient wanderers in the sky. Now, having explored the fire of the inner planets, the grandeur of the giants, the ice of the dwarfs, and even peered to the worlds of other stars, we end with a renewed sense of wonder. The night sky will never look the same. Each dot is a sun, many with planets, some perhaps with beings looking back at a tiny sun pinprick that is our home. The voyage of planetary exploration has really just begun. There are new horizons to reach, literally, as with the probe New Horizons at Pluto, and profound questions still to answer. But one thing is certain: our curiosity will not cease. We will continue to wander, in person or by proxy, mind and body, outward to the planets and beyond. For in seeking these other worlds, we ultimately seek to know ourselves and our place in the cosmos. It is a grand story, one that spans from the fires of creation to the potential spark of life, and it's a story with no end in sight. Each planet we visited, by telescope or spacecraft, has left us changed. They have shown us beauty beyond measure, forces beyond fear, and resilience beyond expectation. In their extremes we find meaning. Mercury's day, night cycle, whispering that too much heat and too little air yields desolation. Venus's clouds warning how quickly paradise can be lost. Mars's dry rivers reminding that climate can turn on a planet. Jupiter's storms humbling us with their power. Saturn's rings teaching the elegance of gravity's order. Uranus and Neptune revealing that even on the edge of darkness, winds still dance. Pluto and its kin proving that even small worlds can be geologically alive. As we continue to learn, we should also take a moment to feel the awe. We are fortunate to live in a time when the long-lost siblings of Earth have been revealed in all their glory. A human from just 100 years ago could only dream of what we've seen. And a human 100 years from now might walk on Mars or float in a Europa submersible, living our present dreams. Our quest for knowledge and exploration binds the generations in a common continuum of discovery. So, step outside on a clear night. Find Venus blazing in the west or Jupiter rising in the east. Know that you're looking at entire worlds, places that we've now touched with our robotic emissaries and, one day, might touch with our hands. The sky that was once the realm of gods and myth is now open to us as a realm of nature to explore. The wanderers are no longer distant mysteries. They are destinations. They have become real places with landscapes and weather and histories we can narrate. And in exploring them, we've woven their stories into our own. We too are wanderers. As Sagan said, we began as wanderers, and we are wanderers still. We have lingered long on the shores of the cosmic ocean, but now we are setting sail among the stars. In the end, the study of planets teaches us humility and unity. All those worlds out there, and here we are, one small crew on spaceship Earth, sailing together through space and time. The pale lights of Mercury, Venus, Mars, Jupiter, and Saturn in our sky are like signposts, telling us where we've been and where we will go. When we finally decipher the secrets of alien atmospheres or find microbes on a distant moon, it will underscore that we are a part of this universe, connected to the planets and stars around us. We are not apart from nature. We are born of the same processes that birthed the planets. The voyage will continue. New rockets, new telescopes, new generations of scientists and explorers will carry the torch. They'll answer questions we haven't thought to ask, and surely encounter surprises we haven't imagined. Planets will continue to fill us with wonder, whether it's weird new exoplanet types or hidden oceans discovered under icy crusts. Each answer will likely raise more questions, as is the way of science. But that is a joy, not a frustration. It means the adventure of discovery is endless. There will always be another horizon, another world to learn from. And as long as humans have eyes to the sky and minds that dream, we will be out there, exploring, moving outward, one world at a time, forging connections across the darkness. In a sense, by exploring the planets, we are the universe exploring itself. Matter that became life, life that became intelligent, now reaching back out to understand the grand mechanism that produced us. Every footprint left on the moon, every photon counted from a distant exoplanet, is the cosmos coming to know itself through us. Our journey through the planets has thus been a journey inward as well, into the nature of who we are and what we may become. When future explorers stand on Mars and look up at a sky with 2 moons, or when a robotic probe sends back the first images from an Earth, like planet light years away, the sense of connection will only grow stronger. We'll realize ever more that we share the universe with all these worlds, and maybe share it with other life. For now, we cherish our pale blue dot while reaching for others. We end our tour back on Earth, gazing up, but with new eyes. The wanderers in the sky are no longer distant gods, but places we know. Siblings in the solar family, each unique, all kin. We have walked among them in our imaginations and through our proxies. Soon, we will with our own feet. The story of planets is ultimately a celebration of human curiosity. We dared to ask ancient lights what they were, and we answered, revealing a universe richer than our ancestors could have believed. Stand under the night sky and feel that connection, tiny though we are. We understand those points of light now. Mercury, Venus, Mars, Jupiter, Saturn. We know them intimately. And far beyond, around myriad stars, countless other planets circle, waiting for our discovery. The wanderers will guide us outward, and wherever we go, we will carry the legacy of understanding forged here at home. In that sense, the journey of exploring planets is a journey of self-discovery for humanity. We set out to find new worlds, and in the process, we found ourselves, one people on one world, learning that the cosmos is full of worlds. It is perhaps the grandest revelation of all. The planets have taught us that the only borders are those we create ourselves. In the cosmos, all worlds share the same sky. The wanderers still move across the heavens as they did for the ancients. But now, when we see them, we greet them as familiar friends, places we've been or soon will go. And as we trace their paths and even send our emissaries to dance among them, we too become wanderers beyond the earth, united in the eternal quest to know the universe and our place within it. The story of planets, our story, continues, onward and outward, under the cosmic sky that we all share. The sun rises in silence, but its presence is a chorus that has echoed through every age of life on Earth. Every morning, its gentle light spills over the horizon and washes the world in gold. In that light lies an ancient promise: warmth to nourish the living, energy to spark the green fuse of plants, and comfort to chase away the chill of night. For as long as creatures have walked under the sky, they have felt the sun's touch and known instinctively that this brilliant star is the giver of life. Yet the sun is more than a kindly nurturer. It is a colossal power, a raging sphere of fire suspended in the darkness of space. From across the cosmic void, it seems tame, a perfect golden disk that rises and sets with reliable grace. But up close, it is wild and untamable, a seething ocean of plasma and magnetic fury. It holds Earth in its grasp, guiding the dance of days and seasons. And it could, in an instant of cosmic anger, scorch our world lifeless. The same sun that gently warms our faces can also unleash deadly radiation and storms of charged particles. It is a giver of life, and it can be a destroyer of worlds. Our ancestors revered the sun as divine, calling it by many names and worshipping its life-giving light. They built great stone circles and temples aligned to its rising, celebrated when it climbed high in summer, and feared its waning in winter. In rare moments, when the sun vanished in a daytime eclipse, they watched in dread and awe as day turned to twilight, praying for the light to return. They sensed its dual nature, its generosity and its danger, even without knowing the science. We now understand that the sun is a star, one among countless others in the galaxy. But to us, it is unique. It is our star, the hearth of our solar system, the steady heartbeat of our cosmic home. It beats silently, a deep thrum of nuclear fires and magnetic pulses that we cannot hear, but that sustains us nonetheless. Every ray of sunlight is a note in that silent symphony, a connection between our small lives and the vastness of the cosmos. Consider this. The light that caresses your skin today began its journey at the core of the sun long before you were born. The warmth on your face is the end of a story that started deep in a stellar furnace. The sun bridges our brief human moment and deep cosmic time. It links the atoms in our bodies to the atoms in distant stars. In its light, we find both our origin and our destiny. We stand in the glow of a cosmic engine, often unaware that above us, a star's turbulent heart is burning and beating ceaselessly. To truly know the sun, we must journey into its very heart. Let us leave behind the blue of our sky and travel inward into the blinding brilliance, into the inner sanctum of our nearest star. What we find there is both humbling and wondrous, a story of creation and destruction, of light and darkness, of a star's life from birth to death. It is, in many ways, the story of ourselves, written in the language of light. Imagine plunging through the sun's surface and journeying toward its center. As we descend, the light intensifies and the heat becomes unimaginable. Deep inside, at the very core of the sun, we enter a realm of staggering pressure and temperature. Here in this stellar heart, hydrogen atoms are crushed together so tightly that they fuse into helium. In that act of fusion, a tiny bit of matter transforms into pure energy, an alchemy that powers the sun. This is the engine of creation hidden in the sun's core. Every second, an immense burst of energy is released, radiating outward to keep the star shining. Gravity presses inward relentlessly, trying to collapse the sun under its own weight, but the fury of nuclear fusion pushes outward, holding the star up. In this balance between gravity and fire, the sun's core burns steadily, a sphere of blazing plasma denser than solid iron and far hotter than any furnace on Earth. The core is a place of extremes beyond our experience. Its light is born in blinding abundance, yet none of that brilliance escapes directly. Only ghostly particles called neutrinos slip away unhindered, streaming out from the core and passing through the sun's layers, and even through our bodies on Earth, as though nothing were there at all. They are the silent heralds of the sun's heart, whispering of the nuclear fires within.
Moving outward from the core, we enter the radiative zone, a vast internal layer where the energy from the core migrates slowly outward in the form of light. Here, photons of radiation ricochet through a dense maze of atoms. A single particle of light, born in the core's fury, may bounce countless times from one atom to another, absorbed and re-emitted in an endless random walk. The plasma in this zone is so opaque and crowded that progress for any ray of light is agonizingly slow. Ages pass as the energy inches its way outward. What we eventually perceive as sunlight on Earth has spent eons fighting its way through this hot, stifling labyrinth. In these deep regions of the sun, energy is transferred not in a simple beam, but like a traveler lost in a thick forest, zigzagging gradually toward freedom. Eventually, the character of the sun's interior changes. Further out, the stellar plasma becomes cooler and less dense, and it can no longer transport energy purely by the random diffusion of photons. At this point, a new process takes over: convection. We have entered the convective zone, the sun's outermost interior layer, where heat is carried upward by the motion of the gas itself. Picture an immense cosmic cauldron boiling slowly. Hot plasma from the layers below becomes buoyant and rises toward the surface, carrying energy with it. Upon reaching higher, cooler regions, it loses heat, becomes denser, and sinks down again to be reheated. These rolling currents form giant looping cells of plasma the size of continents, rising and falling in rhythmic surges. Through the convective zone, energy that once took millennia to crawl outward now surges toward the surface in a matter of mere weeks, riding the updrafts of this titanic, boiling motion. At last, the energy reaches the visible surface of the sun, the photosphere. This is the layer where the sun's light finally escapes into space and shines freely across the solar system. To our eyes, the photosphere is the sun's radiant face, a glowing golden disk with a sharply defined edge. Up close, it would not appear smooth at all, but finely textured and ever-changing. The surface seethes with the imprint of the convection below, a pattern of granules, like a vast mosaic of luminous cells. Each granule is the top of a convective plume, a cell of hot plasma rising from the depths. Their centers glow bright and white-hot, where fresh energy wells up, and their edges darken to a deeper amber, where cooler plasma is sinking back down. This granular pattern continually shifts and reforms, as though the sun's face is a living, boiling sea of light. Here and there, the photosphere is marred by dark blemishes, sunspots. These spots are cooler than their surroundings, and so they appear nearly black against the brilliance of the sun's face. A sunspot is born from the sun's magnetic mischief. Intense magnetic fields well up from inside the sun and suppress the hot rising gas, creating a region that is slightly less hot and thus darker. Sunspots can grow to be larger than the entire Earth, and may last for days or weeks before dissipating. They are a sign that the sun's magnetism, though invisible, is ever present, knitting itself into the solar surface. We will soon see how these magnetic forces can erupt in violence, but for now, standing at the surface of the sun, we behold a roiling ocean of fire extending in all directions, a vista of constant boiling creation. Peering at the sun's face with sensitive instruments, we find that it is also vibrating subtly. The boiling convection within causes the sun to ring like a resonant bell. Its surface shivers in patterns, waves traveling across and through the sun, making the whole star gently pulse. Astronomers use these pulsations, this music of the sun, to probe its interior, much as one might learn the shape of a bell from the sound it makes. Through this solar symphony, we can discern the flowing currents deep inside, the building magnetic fields,
and even hints of the sun's core, all hidden beneath the blinding glare. Rising above the photosphere, the sun's atmosphere continues outward in layers of increasing mystery. Just above the visible surface lies the chromosphere, a tenuous veil of gas that appears as a faint, pinkish glow. Here, the temperature, which had cooled at the photosphere, begins to climb once more. The chromosphere is like the sun's shimmering halo, visible clearly only when the bright photosphere is hidden during a solar eclipse. In those rare moments, it can be seen as a thin rim of ruby light encircling the moon's silhouette. Within the chromosphere, slender jets of plasma, called spicules, continually shoot upward, each one ephemeral and short-lived, lasting only minutes before falling back. The chromosphere is a restless transitional zone, a place where the fury from below meets the stillness of space above, and the solar atmosphere prepares for an abrupt and profound change. Above the chromosphere lies the sun's crown, the corona. Faint and otherworldly, the corona is a vast halo of pearly light that surrounds the sun and stretches far into space. It is breathtakingly beautiful and enigmatic, revealed to human eyes only during a total solar eclipse, or through specialized telescopes that block the sun's glare. In those brief eclipse moments, when daytime twilight descends and the moon hides the sun's brilliance, the corona appears as a pale, white aura, etched with luminous streamers and delicate filaments extending in all directions. But the corona is not merely a spectacle of light, it is a furnace in its own right, one far hotter than the sun's surface below. While the sun's photosphere is blisteringly hot, the corona above is unimaginably hotter, a puzzling reversal of what one might intuitively expect. In this outermost layer, the sun's magnetic field rules supreme, shaping the thin gases into graceful loops and arching structures. Great magnetic arches rise high above the sun, filled with incandescent plasma that traces the invisible lines of force. The corona is incredibly thin, its particles so sparse that if you were standing in it, shielded somehow from the heat, you might not even notice the few atoms brushing by. And yet, despite its tenuousness, the corona possesses immense energy and reaches temperatures of such magnitude that scientific instruments must strain to record them. Why does the corona burn so fiercely? It remains one of the sun's lingering mysteries. Perhaps the sun's tangled magnetic fields thrash and snap, heating the gas in a myriad of tiny explosions, or waves of energy ripple outward from the sun's surface, dumping heat into the corona. Whatever the cause, the sun's crown glows with an ethereal fire that science is still striving to fully understand, a reminder that even our well-known star holds secrets at its heights. At the edge of the corona, the sun begins to fade into the darkness of space. There is no sharp boundary where the star ends. Its atmosphere simply thins into the void. Here, the corona gives birth to the solar wind, a ceaseless stream of charged particles, electrons and protons, that flows outward in all directions. The sun, in effect, is always breathing out. Its breath is the solar wind, and it carries a piece of the sun's essence out to the farthest planets and beyond. The gravity that so overwhelmingly confines the core cannot hold these fast, lightweight particles of the corona. They race outward along open magnetic lines, escaping the sun's grip. The solar wind is, in a sense, the sun's extended atmosphere flowing freely into space, filling the solar system like an invisible, ever-expanding bubble. We have now traveled from the sun's core, where matter becomes energy, to the wispy fringes of its corona, where the star dissolves into the broader cosmos. In this journey, we have witnessed the anatomy of a star, its layered realms, each with its own wonders. We have seen the ferocious furnace at its center, the slow upward struggle of light, the boiling convection that brings energy to the surface, the radiant face shining into space, and the crown of fire that reaches beyond the sun itself. Yet the sun is far from a static ball of gas. It is dynamic and alive, its surfaces and atmosphere writhing with magnetic fields and sudden eruptions. To truly understand our star, we must explore these invisible forces that bind and sometimes unravel the sun's material. We must watch as the sun's calm radiance is punctuated by storms, blazing flares, erupting prominences, and billowing clouds of plasma that can span millions of miles. It is time to examine the sun's magnetic heart and the space weather it breathes into the solar system. Beneath the sun's bright face lies an unseen web of forces that drives its most dramatic behavior. The sun is a giant magnetic dynamo. As it spins on its axis and its plasma churns, it generates magnetic fields that thread through its interior and arch out into space. Imagine lines of unseen force looping out from the sun's depths, arcing high above the surface and diving back down. These magnetic field lines become twisted and tangled by the sun's constant turning and boiling. Where they burst through the surface, they drag up or suppress hot plasma, creating the dark sunspots we see freckling the photosphere. Every feature we observe on the sun, its spots, its flares, its glowing coronal loops, is shaped by magnetism. Without the magnetic field's influence, the sun would be a far more monotonous star. Instead, magnetism makes it a living, breathing, and sometimes tempestuous entity. Sunspots are the most visible signs of the sun's magnetic moods. They tend to appear in groups, often as pairs linked by a great looping magnetic field. One spot will have a north magnetic polarity, the other a south, like opposite poles of a bar magnet. The arc of magnetism connecting them traps cooler plasma in its grip, outlining structures we sometimes see as prominences, towering loops of glowing gas that stand above the sun's surface. Sunspots grow and shrink as the magnetic fields beneath them strengthen or decay. Over days or weeks, a complex sunspot group may evolve. An enormous energy builds up in its tangled magnetic knots. There is a rhythm to these appearances. Roughly every decade or so, the sun swings from a time of few sunspots to a time of many, and back again. At the peak of this cycle, dozens of spots can dance on the sun's face. At the low point, the sun's visage is often clear and quiet. Each cycle, the sun's magnetic poles even flip. North becomes south, and south becomes north, as part of this regular heartbeat of our star. Our sun, like a living thing, has its seasons of storm and calm. When the stress in twisted magnetic field lines becomes too great, they can suddenly snap into a new shape, much like a tensed rope that finally breaks free. In that instant, the energy that was bottled up in the field is explosively released. This is a solar flare. On the sun's surface, a flare is a blinding flash of brightness, a sudden blaze of radiation across the spectrum. It is as if a patch of the sun's surface has detonated with the power of countless nuclear bombs. In minutes, a flare unleashes a torrent of X-rays and charged particles into space. If the Earth lies in its path, these emissions race toward us at light speed, arriving just minutes after the flare erupts. Our planet's upper atmosphere suddenly swells with energy. Radio communications can crackle and fade as the ionosphere, the atmosphere's charged upper layer, is pummeled by the onslaught, and astronauts in orbit might hastily seek shelter from a burst of radiation that moments before was not even known to exist. Flares are often accompanied by an even more massive eruption, the coronal mass ejection, or CME. Where a flare is a flash of light and high-speed particles, a CME is a giant cloud of solar plasma hurled out from the sun. When a particularly complex magnetic loop in the corona destabilizes, it can fling away a chunk of the sun's outer atmosphere entirely. Imagine a colossal bubble of electrified gas, more massive than all of Earth's oceans combined, suddenly launched into space and expanding as it races outward. A coronal mass ejection can contain an astonishing amount of matter and energy, an immense, billowing storm front in the emptiness of space. If one of these solar tsunamis is aimed toward Earth, we will know it soon enough. Within a day or two of the eruption, the wave of solar particles reaches our planet. Earth's magnetic field recoils and reverberates from the impact, like a bell struck by a hammer. We call this disturbance a geomagnetic storm. When a geomagnetic storm engulfs Earth, the results can be both beautiful and dangerous. Under the night skies at high latitudes, ghostly lights burst forth. Auroras, the northern and southern lights. Normally, auroras are confined to the polar regions, tracing the shape of Earth's magnetic field as it directs the sun's particles toward the poles. But during a strong solar storm, auroras can be seen much farther from their usual homes, painting the skies in eerie greens, purples, and reds over a vast swath of the world. Imagine waking in the tropics to find the night sky alive with rippling curtains of light. Such an astonishing sight has indeed occurred when the sun lets loose one of its great storms. In ages past, people who witnessed auroras far from the poles were often terrified. They saw in them dragons or celestial armies, believing the heavens were aflame with omens. To ancient peoples, these luminous dances in the sky must have been both wondrous and terrifying. Even today, knowing their true cause, one cannot watch the aurora's shimmering display without a feeling of reverence for the forces at play. Yet along with this beauty comes disruption. The same geomagnetic tempest that sets the skies aglow can wreak havoc on our modern technology. The barrage of charged particles and the distortion of Earth's magnetic field can induce surges of electric current in long conductors here on the ground. In our age of wires and wireless signals, a strong solar outburst can interfere with radio transmissions, scramble GPS navigation, damage satellite electronics, and even overload power grids, plunging cities into darkness. Over a century ago, a monumental solar storm made telegraph lines spark and catch fire. Telegraph operators found they could disconnect their batteries and still send messages. So powerful were the electrical currents coursing through the wires. If a storm of that magnitude struck today, satellites might be knocked offline, and extensive blackouts could occur. For all our technological might, we remain passengers in the sun's domain, subject to its occasional fits of violence. This turbulent interplay of solar magnetism and its effects on Earth and the planets is what we call space weather. Like weather in Earth's atmosphere, it has calm days and tempestuous days. The sun's magnetic field is ever shifting, and as it does, it breathes out gusts and squalls into the solar system. Most of the time, the solar wind blowing past Earth is a gentle breeze, and our planet's magnetic field shrugs it off with little fanfare. But when the sun erupts, the space around Earth becomes a stormy sea. A surge of charged particles and magnetic disturbances crashes against our planet's defenses, and near-Earth space itself reacts in kind. Auroras lighting up, satellites feeling the shock, currents coursing through the ground below, where all seems quiet. Fortunately, Earth has a sturdy shield. Our planet's magnetic field envelops us, carving out a protective bubble that the solar wind must flow around. This magnetosphere diverts most of the charged solar particles, allowing only a portion to funnel down toward the poles. In the clash of sun and Earth, the auroras are the glowing traces of our magnetic shield intercepting the solar storm, a testament to the protection it offers. Planets without a significant magnetic field, like Mars, have no such guard. Over eons, the sun's relentless particles stripped away much of Mars's atmosphere, leaving it a cold, arid world. In that fate, we see mirrored the dual nature of our sun, the gentle provider that sustained life on Earth, and the relentless force that can erode a planet's very sky. It nourished Earth with light and warmth, while its winds slowly wore Mars down. Magnetism is the hidden architect of the sun's behavior, from the steady cycle of sunspots to the wild drama of flares and auroras. Through it all, the sun continues to shine steadily in our sky, a reassuring beacon of day. But we have learned that beneath that steadiness is a flickering heart of magnetic energy. The sun's calm and its storms are two sides of the same coin, both born from the same stellar heartbeat. As humanity extends its reach into space and relies ever more on technology, studying and forecasting this space, weather becomes increasingly important. We now watch the sun with eyes open, tracing its spots and flares, listening for the whispers of its solar wind. We have even sent spacecraft to touch the sun's fringes, sampling its corona and feeling its magnetic embrace, all to better understand our star's moods. In the midst of these stellar tempests, it is easy to lose sight of the sun's most gentle and steadfast gift, the sunlight itself. Every day, countless photons leave the sun and stream across space, and some of those reach our world to illuminate the sky. Consider for a moment a single particle of light, a photon, born in the sun's core. It began as pure energy released by a fusion reaction in that dense, searing heart. For untold years, it fought its way through the sun's interior, scattering and dancing through the radiative maze, slowly migrating to the surface. At last, it broke free from the photosphere, joining the radiant tide of sunlight that floods out into the darkness. In that instant, it set out across the cosmic gulf at the ultimate speed, racing through the vacuum toward our small planet. After a brief voyage through the abyss of space, the photon pierces Earth's upper atmosphere. Perhaps it is dawn, and this tiny messenger of the day slips through a clear sky to reach a waiting leaf on a tree. The photon is absorbed, its energy triggering the chemistry of life, photosynthesis, helping a green leaf turn carbon dioxide and water into sugar. In that moment, a bit of the sun's energy, carried across the cold void by a single photon, becomes part of a living plant. Another photon falls upon a human face and is absorbed in the warm skin of someone standing under the morning sun. Nerves register the gentle heat. The mind welcomes the comfort. That warmth is a direct touch from our star, a tangible link between our flesh and the nuclear fires at the sun's heart. Every ray of daylight that we see, every soft beam reflected by the moon at night, began in the sun's core long ago. The sunshine that makes the petals of a flower glow, that draws a child's laughter on a bright afternoon, that dances on waves at dusk. All of it is energy forged in a star and sent outward as a gift across the emptiness. It is literally starlight. The light sustains the winds and rains of Earth's weather, drives the engines of life, and paints our world in color each sunrise and sunset. From the sun's perspective, these photons are a way it reaches into the darkness, touching worlds with its essence. From our perspective, they are life and time itself. Every meal we eat is sunlight captured by plants. Every sight we behold is enabled by the sun's illumination. Thus, the sunlight we feel on our skin carries an ancient story. It is the end of a journey that began in the heart of a star and a bridge between our everyday lives and cosmic processes. In that golden glow, the tumult of the sun's interior and the fury of its storms are gentled into a nurturing radiance that gives life rather than takes it. We are, in every sense, bathing in the light of a star. To stand in the sunshine is to be touched by the cosmos, to be warmed by a process that has been ongoing for eons. The next time you see dust motes dancing in a sunbeam or feel the sun's warmth on your face, remember that you are feeling the afterglow of a journey that spanned the depths of space and countless years, a journey from the core of a star to the core of your being. Beyond the orbit of Earth, the sun's influence continues in a quieter but no less significant form. The solar wind that billows out from the corona fills the solar system with a tenuous, invisible presence. Space is not truly empty. It is filled with the sun's breath. This stream of charged particles flows outward past all the planets, carrying with it a stretched-out imprint of the sun's magnetic field. It's as if the sun, through its wind, reaches out to touch each world in its orbit, linking them in a web of invisible threads. As the solar wind encounters each planet, the effects depend on whether the planet is protected by its own magnetic field or left exposed. We've seen how Earth's magnetic bubble deflects the wind, diverting the charged particles around us. Jupiter and the other giant planets have formidable magnetic fields that carve out even larger sanctuaries in the solar wind. When the solar wind presses against these magnetic bubbles, it sparks auroras at their poles too. Jupiter's polar skies glow with curtains of light far more intense than Earth's, and even Saturn wears ethereal rings of auroral light. On worlds like Mercury or our Moon, which have little or no magnetic shielding, the solar wind slams directly into the surface. It can embed particles in the soil and slowly sputter away atoms into space. Mars, with only patchy magnetic fields and a thin atmosphere, has its skies occasionally set aglow by diffuse auroras, a reminder that even without a strong magnetosphere, the solar wind still makes its presence known. Perhaps the most visually stunning evidence of the solar wind's reach is found in comets. When a comet from the frigid outer reaches of the solar system ventures close to the Sun, it sprouts a luminous tail that always points away from the Sun. This is because the solar wind, along with the gentle pressure of sunlight, is pushing material off the comet's nucleus and sweeping it into a tail that streams far into space. Every comet's tail is essentially a windsock, revealing the direction of the Sun's breeze. In ancient times, people saw those mysterious comets with their glowing tails stretching across the sky, and perhaps sensed that the Sun and the comet were interacting. Now we know it is the breath of the Sun, gusting through space, that draws those ephemeral streaks. The solar wind is not a steady, featureless breeze. It has structure and gustiness. Fast streams of solar wind can overtake slower ones, creating turbulent regions out in the depths of space. Magnetic clouds and shock waves from solar eruptions course through the wind, eventually overtaking planets or other spacecraft that lie in their path. The wind also carries the Sun's magnetic polarity outward. At times, Earth finds itself connected to the Sun by magnetic field lines stretching across interplanetary space, allowing energetic particles from solar flares to spiral directly toward us. In this way, the solar wind is the medium that transmits the Sun's influence throughout its domain, like a great cosmic ocean in which the planets sail. As our solar system journeys around the center of the Milky Way, it carries this protective bubble along. The Sun, like a bee in a giant swarm, orbits the galactic core among billions of other stars. One lap around the galaxy takes an unimaginably long time. In the Sun's long life so far, it has only managed a few dozen such circuits. On this grand voyage, our star drifts through changing cosmic neighborhoods. Sometimes the space around it is relatively empty. At other times it might encounter wisps of nebulae, or the lingering echoes of ancient supernovae. These encounters can subtly influence the boundary of our heliosphere, perhaps even nudge comets from the distant cloud at the fringes of our solar system. We ride along on this stellar odyssey, a family of planets wrapped in the Sun's embrace, cruising through the galaxy's spiral arms. It is a humbling thought that our entire existence, every life, every story told under the sun, has been carried on this great galactic journey, and it will continue long after we are gone, the Sun forging ahead through the dark with its tiny companions in tow. Eventually, at some immense distance from the Sun, the solar wind begins to meet resistance. The sparse gas that drifts between the stars pushes back against the Sun's advancing wind. The solar wind slows, compresses, and finally, at a certain boundary, it can push no further. The continuous expansion of the Sun's atmosphere is halted by the presence of the wider galaxy. This boundary marks the outer edge of the Sun's influence, the frontier of our star's dominion. Here, the solar wind's long journey ends, merging into the interstellar medium. This invisible border, defines a vast bubble around the Sun, known as the heliosphere, a cocoon of solar particles and magnetic fields that envelops all the planets. To step outside that bubble is to enter truly interstellar space. For decades, the solar wind was only a theory, an idea to explain why comet tails always point away from the Sun. It wasn't until humanity ventured into space with probes that we felt this wind firsthand. Our spacecraft have measured its particles and tasted its composition. Finally, after decades of journeying, a tiny spacecraft built by human hands passed through the boundary of the heliosphere and sailed into interstellar space, becoming the first emissary from Earth to enter the realm between the stars. It confirmed the existence of that distant frontier and carried with it a golden greeting from our world as it moved under the dim light of a sun now far behind. The sun's breath, it turns out, has a limit. Within that limit, within that bubble, the sun is Lord and life-giver. Every world we have ever known lies inside this protective sheath blown by our star. Now, standing at the edge of the heliosphere, we gaze outward and backward, outward to the realm of the galaxy beyond, and backward toward the sun at the center of its bubble. We can appreciate the true scale of our star's influence. The sun is not just a disk in our sky. It commands a vast region of space, sculpting it with light and wind. It has forged a safe haven in the galactic sea, a place where its family of planets resides. To understand the sun fully, we must also understand how stars like it are born and how they die. For our sun is one among billions, each with its own story of origin and fate. Our journey now moves beyond our solar system, beyond the present moment of our sun's life, to the story of how such stars come into being and how they transform over time. Stars are born in darkness, far from the bright bustle of any galactic core, in the quiet spiral arms of galaxies like our Milky Way. Vast clouds of gas and dust drift in cold obscurity. These are the stellar nurseries, enormous nebulae stretching across light years of space, rich in hydrogen and sprinkled with heavier elements forged in ancient supernovae. Within these great clouds, gravity works patiently and silently. A slight densification, perhaps triggered by the shockwave of a distant exploding star or the brushing encounter of two clouds, begins to draw matter toward its center. As the gas compresses, it heats up and starts to glow faintly. What was once invisible in the darkness becomes a warm ember hidden inside a cocoon of dust. This is the birth of a star, or rather, the first whisper of a star yet to be. As the cloud fragment collapses under its own weight, it often breaks into smaller pieces, each destined to form a star, or even a small cluster of stars. In each fragment, matter spirals inward, and as it falls, it begins to spin faster, like a twirling ice skater pulling in her arms. A flattened disk of gas and dust forms around the growing central mass, whirling like a carousel. At the center of each collapsing fragment, a protostar, a baby star, is taking shape. It is not yet a true star, for it has not begun nuclear fusion, but it shines with the heat of its gravitational contraction. We can imagine it as a glowing orb buried deep within a dusty womb. If we could pull back the veil of dust and look inside, we would see a scene both serene and violent. The protostar's surface roiling with convection, jets of gas erupting from its poles and piercing out into space, and the surrounding disk feeding material steadily onto the growing stellar infant. In these concealed cradles, many stars are often born together, siblings in a stellar brood. Some are destined to be massive and brilliant, others small and faint. For a brief time, the protostar continues to gather mass. The infalling gas rains down mostly onto the disk, which then funnels onto the star. The star grows, and the pressure and temperature at its center climb ever higher. When the core temperature at last soars to the threshold, where hydrogen atoms begin to fuse into helium, a profound transformation occurs. The protostar becomes a star, It is as if a switch is flipped in its core. The darkness inside ignites into light. The star begins to generate its own energy by the same nuclear process that powers our sun, and a new sun bursts into existence in that once dark place. With that first ignition of fusion, a stellar wind, much like the solar wind of our sun, often springs from the newborn star, and intense light from the hot young star pours into the surrounding space. These forces blow away the remaining shreds of the natal cloud, dispersing the cocoon that once hid the star. If the star is massive enough, its fierce radiation may carve fantastic shapes in the parent nebula, creating glowing cavities and pillars of dust that resist the onslaught for a time. Before long, what was once an opaque dark cloud becomes a cluster of shining new stars, its birth cloud eroded to wisps around them. The siblings now bask in each other's light as they drift together, loosely bound by gravity. Our own sun was likely born in such a cluster of stars. It may have had many siblings forming alongside it in a long-vanished nebula, all of them cocooned together and then emerging into the galaxy's light. In that stellar nursery, the sun's siblings would have shone nearby, sharing a common region of space for a time. But over the ages, the cluster dispersed. Each star, including our sun, went its own way, moving through different orbits around the Milky Way. Today, the sun's sisters and brothers are scattered, indistinguishable from the other stars of the galaxy, though astronomers scanning the sky have identified a few stars with chemical fingerprints so similar to the sun's that they might be long-lost solar siblings. In the collapse of a nebula and the birth of a star, we see nature's cycle of creation at work. The gas and dust that form new stars carry the ashes of previous generations, the carbon that will someday course through the veins of living creatures, the oxygen that will fill their lungs, the silicon that will form rocky worlds. All these atoms were fused in stars that lived and died before our sun was born, then mixed into the clouds from which new stars arise. Each generation of stars enriches the galaxy further, seeding the raw material for planets and life. Thus, when a new star like our sun ignites, it carries within it the legacy of cosmic ancestry. Around many newborn stars, the leftover gas and dust in the disk coalesce into smaller clumps, giving birth to planets, moons, comets, and asteroids, the makings of a new solar system accompanying the new sun. From afar, a stellar nursery like the Orion Nebula offers us a glimpse of this wondrous process. Through telescopes, we see stellar embryos still swaddled in dust, others breaking free and burning blue-white with youthful energy. We see great columns of dark gas, cosmic pillars, being eroded by the radiation of hot young stars hidden within them. In that radiant chaos, worlds are being formed, and light that will shine for billions of years is first kindled. Star birth is at once delicate and cataclysmic. Delicate in the slow, inexorable gathering of a star's first light, and cataclysmic in the way a newborn star's brilliance can rip apart the very cloud that gave it life. From these nurseries emerge all stars, whether destined to be mighty blue giants or dim red dwarfs. The process is the same, guided by the pull of gravity and the laws of physics that govern heat, pressure, and fusion. We have journeyed from our sun's neighborhood out into the broader galaxy to witness the origin of stars. Now, having seen how stars take their first breath, we can explore the grand tapestry of stellar variety, the many kinds of stars that fill the cosmos, from the smallest embers to the most luminous beacons. The stars that populate the universe are as diverse as the creatures in a great ocean. They come in different sizes, colors, and brightnesses, each type with its own character. Astronomers classify stars by their temperature and luminosity, which often correlates with color. Just as iron glowing in a blacksmith's forge changes from dull red to orange to white hot as it gets hotter, a star's color tells us its heat. The coolest stars are deep red, smoldering with a subdued cherry glow. Hotter stars shine in yellow and white hues. The very hottest stars blaze with blue-white brilliance, their surfaces incredibly hot. The smallest true stars in the cosmos are the red dwarfs. These diminutive stars contain only a small fraction of the sun's mass and glow feebly, often with a light so faint that none are visible to the naked eye from Earth, despite being the most numerous stars in the galaxy. A red dwarf is usually much smaller and cooler than our sun, giving off a ruddy light. But what they lack in brightness, they make up in longevity and ubiquity. The vast majority of stars in the Milky Way are thought to be red dwarfs, quietly burning their fuel at a glacial pace. A red dwarf may live for an almost eternal span of time before it runs out of fuel. In these diminutive furnaces, the flame of nuclear fusion is weak but extraordinarily steady. Some of the smallest red dwarfs can continue to shine for longer than the current age of the universe. On the other end of the stellar spectrum are the blue giants and supergiants. These stars are born with many times the mass of the sun. They are extremely hot and brilliant, shining with a fierce blue-white light that can be seen across great distances. A blue giant star pours out an enormous amount of energy, consuming its hydrogen fuel at a prodigious rate. Because of this, its life is intense and fleeting. It will exhaust its core fuel in a cosmic eye blink, a mere moment compared to the tranquil longevity of a star like our sun. Some of these massive stars do not stay blue-white for their whole lives. As they age, they swell and cool, turning into red supergiants that can be truly colossal in size, their bloated atmospheres expanding outward to stupendous dimensions. Imagine a star so large that, were it placed where our sun is, it would extend beyond the orbit of Earth and well into the realm of Mars. These red supergiants glow with a cooler, reddish light, but they are tremendously luminous due to their sheer size. They are rare and splendid beacons in galaxies, heralds of impending cosmic change, for they live fast and die spectacularly. Between these extremes lies a rich variety of stars. There are orange dwarfs, slightly smaller and cooler than the sun. There are white stars, somewhat hotter and more massive than the sun. And there are stars like our own, yellow-white and medium-sized, often called main sequence stars or dwarf stars by astronomers. Our sun, in fact, is considered a dwarf star in this sense, not because it is especially small, it is larger and more massive than most stars, but because it is in the prime of its life, steadily fusing hydrogen in its core. It hasn't yet bloomed into a giant. In terms of mass and brightness, the sun is fairly average, but because the faint red dwarfs are so inconspicuous to our eyes, most of the individual stars that dazzle us in the night sky are actually more luminous than our sun. Many of the bright stars we see at night are larger, hotter, or more energetic than the sun, which is why they stand out from afar. Meanwhile, countless dim red stars nearer to us go unnoticed without a telescope. Stellar classification also includes exotic categories. There are the supergiants we mentioned, both blue and red, which are essentially stars on steroids, far larger and more luminous than ordinary stars. And there are stars at the very brink of not being stars at all, the brown dwarfs, sometimes nicknamed failed stars. These objects form in the manner of stars but do not accumulate enough mass to ignite sustained hydrogen fusion in their cores. A brown dwarf glows faintly with leftover heat from its formation, and perhaps with brief flashes of fusion of heavier forms of hydrogen, but it gradually cools and fades, acting more like a giant planet than a true star. Brown dwarfs fill the gap between the largest planets and the smallest red dwarfs, and they add to the menagerie of objects in the galaxy. Nature produces stars in a continuum of masses and sizes, from tiny red embers that burn for practically eternity to stellar titans that blaze with incredible intensity and then perish in the blink of an eye. Each type of star has its own destiny. A star's mass, set at birth, is the key that unlocks the rest of its life story. With a high mass comes a glorious but short-lived existence as a giant, likely ending in a dramatic explosion. With a low mass comes a long, steady burn and a quiet retirement. Having surveyed the variety of stars, the small, the medium, the great, we can now follow one typical star, perhaps not unlike our sun, through the stages of its life, from its youthful radiance to its final farewell. Let us trace the fate of a star much like our sun, now that it has burned in the heavens for eons. For a long time, such a star shines steadily, fusing hydrogen into helium in its core and bathing any nearby worlds in stable light. But the fuel at its center is finite. Eventually, after many billions of years of shining, the hydrogen in the core dwindles. The balance that sustained the star for so long begins to tip. With less fusion to support it, the core of the star starts to contract under its own gravity. As it contracts, it heats up, much as a bicycle pump grows warm when you compress the air inside. This extra heat flows into the shell of hydrogen that surrounds the inert core, a shell that still has hydrogen left to burn. And then something dramatic happens. Hydrogen in this outer shell, now at extreme temperatures thanks to the contracting core beneath, ignites in fusion. The sudden onset of shell burning causes the star's outer layers to push outward. The star swells enormously in size, turning into what we call a red giant. Its surface cools as it expands, shifting from yellow-white to orange-red. But the star's interior becomes hotter than ever, and its luminosity soars due to its sheer size. Our once modest sun-like star becomes a bloated colossus. In this red giant phase, the star's radius can grow far larger than it was in its youth. If our sun were to undergo this transformation, it would likely engulf Mercury and Venus, and perhaps even Earth, turning those worlds into charred cinders swallowed by the expanding stellar fire. The sky of any surviving outer planets would be dominated by the star's enormous disk, a brilliant coppery orb covering a huge swath of the heavens. Deep inside the red giant, the core continues to shrink and heat, as it is now made mostly of helium ash, the byproduct of those long ages of hydrogen fusion. When the core grows hot enough, a new kind of fusion begins. Helium atoms start fusing together to form carbon and some oxygen. Our star, which was facing death, finds a second wind. The onset of helium fusion in the core, often beginning in a sudden burst for a sun-like star, something astronomers poetically call the helium flash, stabilizes the star for a time. The core expands a little and cools, and the star's bloated outer layers contract somewhat from their extreme size. The star settles into a new equilibrium, a helium-burning giant. In this phase, the star's color might become a bit more yellowish as it slightly shrinks, and its surface temperature rises again, and it burns steadily once more, though its remaining lifetime is now comparatively brief. But helium, too, is a finite fuel. In time, the core's helium is exhausted, leaving an inert mass of carbon and oxygen, the carbon and oxygen that were created by the helium fusion. For a star like our Sun, no further fusion is possible in the core. The temperatures required to ignite carbon are beyond its reach. With fusion ceasing again in the center, the core of the star, now a dense ball of carbon and oxygen, contracts yet further. Meanwhile, helium fusion may continue in a shell around the core, with hydrogen fusion still going in a shell above that for a while. This causes the star to swell once more, even larger than before. The giant star becomes highly unstable in this final stretch of its life. It pulsates, growing and shrinking, trying to find balance, but never quite succeeding. Each expansion and contraction shakes loose some of the star's outer layers. Gentle at first, these pulsations turn into violent throes that throw vast clouds of the star's outer atmosphere into space. The star is literally coughing away its own substance, shedding its mass like tears into the void. Eventually, the entire outer envelope of the star is cast off, blown away into space as a gorgeous gossamer shell of gas. For a brief time, that expanding shell is illuminated by the hot, exposed core at the center, and it shines as a glowing, multicolored cloud known as a planetary nebula. To an observer afar, it is a sight of eerie beauty. A round or ring-shaped mist, glowing where once there was a star, often with intricate patterns like delicate rings or hourglass forms. This is the dying breath of a star like the Sun, a final gesture of beauty as its outer layers, now free in space, fluoresce in the stellar twilight. What remains of the star itself is the central core, now revealed, a ball of carbon and oxygen about the size of Earth, tremendously hot but no longer sustained by fusion. This is a white dwarf, the ember of a star's heart. It glows white-blue with residual heat, initially extremely hot, though its small size means its total light output is relatively modest. A white dwarf is one of the strangest forms of matter in the universe. It is supported not by heat or ongoing fusion, but by the quantum pressure of electrons, a fundamental resistance of matter to further compression. Its density defies imagination, the mass of a sun compressed into a sphere the size of a planet. A spoonful of white dwarf material would outweigh a mountain. In this exotic, degenerate state, the stellar core will sit and slowly cool for time spans beyond human comprehension, fading from white to yellow to red, and eventually toward blackness. Thus ends the life of a sun-like star, not with a bang, but with a serene, farewell glow. The mighty red giant's cast-off shroud becomes part of the galaxy, seeding space once more with elements like carbon and oxygen that will one day find their way into new nebulae, new stars, new planets, and perhaps new living beings. The white dwarf that remains is like a stellar tombstone, an extremely dense crystal of carbon and oxygen. Some have likened a white dwarf to a cosmic diamond, marking where a shining sun once lived. Over eons, it will cool further and dim, eventually becoming a black dwarf, a hypothetical cold dark sphere, the final quiet cinder of a once radiant star. The universe, however, is not yet old enough for any white dwarfs to have cooled completely to black. That final stage lies in the far future, far beyond the present age of the cosmos. Our sun will one day follow this very path. It is the destiny of all stars in its weight class. But not all stars share the same fate. The most massive stars, those bright blue giants we discussed, live dramatically different lives and meet far more violent ends. Before we return to the personal tale of our own sun's future, let us first briefly touch on the spectacular final act of those heavier suns, a fate that leaves behind some of the most enigmatic objects in the cosmos. While a star like the Sun ends its life in relative peace, the same cannot be said for the giants. The most massive stars go out with staggering violence. After burning through hydrogen and helium in a cosmic rush, a high-mass star, far more massive than our Sun, doesn't stop at carbon and oxygen. Its core, under tremendous gravity, continues fusing heavier and heavier elements in layers, like the layers of an onion. Carbon fuses into neon, neon into oxygen, oxygen into silicon, each stage burning faster and yielding less energy than the last. Finally, the core is transmuted into iron, the ash of nuclear fusion, an element that cannot release energy by fusing further. When enough iron accumulates in the core, the star faces an irreversible crisis. With no new energy to support it, the iron core collapses in on itself in a fraction of a second. The core implodes, and densities reach such extremes that atoms are crushed. Protons and electrons melt into neutrons. The core, which was once perhaps the size of Earth or smaller, shrinks to a sphere only a few miles across in an instant. In that moment of collapse, a phenomenal amount of gravitational energy is released. The infalling outer layers of the star hit this super-dense core and rebound outward in a titanic explosion, a supernova. The star's death throes are so violent that for a brief time, the exploding star can outshine all the billions of other stars in its galaxy combined. The supernova blasts the star's outer layers into space at incredible speeds, and shockwaves race through the expanding debris. Temperatures in the explosion briefly soar so high that elements heavier than iron are forged in the fiery crucible. Gold, silver, uranium, and many others are synthesized in those final furious seconds. These newly minted atoms are hurled into the cosmos to mingle with the gas and dust that will eventually form new stars and planets. What remains at the center of this cataclysm is the collapsed core. If the star was only moderately massive, on the lower end of the massive star range, the core's collapse is halted by the pressure of densely packed neutrons. Matter squeezed so tightly that the neutrons resist any further compression. The core becomes a neutron star, an object of incredible density and exotic nature. A neutron star packs more mass than our Sun into a sphere only a few tens of miles wide. It is essentially a giant atomic nucleus, a ball of neutrons left behind by the supernova. A thimbleful of neutron star material would outweigh a mountain. Neutron stars often spin rapidly. The parent star's rotation speeds up dramatically as it collapses, like a pirouetting skater pulling in her arms, and they may possess intense magnetic fields. Some neutron stars sweep beams of radiation from their magnetic poles as they spin, like lighthouses in the cosmos. These are observed as pulsars, blinking radio or X-ray beacons, marking the location of a neutron star across the galaxy. For the most massive of massive stars, even neutron degeneracy pressure cannot hold the core up. If the collapsed core is above a certain critical mass, nothing known can stop its collapse. It continues to shrink until it essentially vanishes from view, forming a black hole. In that case, the stellar remnant has crushed itself into a point of virtually infinite density, enveloped by a region of space from which nothing can escape. Not even light can climb out of the warped space around the collapsed core, hence the name black hole. What was once the heart of a star becomes a kind of cosmic abyss, a pit in the fabric of the universe. A black hole can be thought of as the star's ultimate tombstone, carrying its mass hidden within a distortion of space-time. We infer its presence only by ghostly tracers, the desperate whirl of gas and dust spiraling into invisibility, flaring in X-rays as it vanishes, or the subtle quivering of space-time itself when the black hole is jarred by the fall of something massive. When a supernova finally fades, it leaves behind these strange remnants, a neutron star or a black hole, and an expanding cloud of gas and dust that was once the star's outer layers. In time, that cloud will cool and disperse into the interstellar medium. The elements cast into space will blend with other matter and eventually become part of new stars, new planets, and perhaps new life. Massive stars, though few in number compared to red dwarfs, are the great alchemists and fireworks of the universe. In dying, they sow the heavy elements across the galaxy, the very elements that make rocky planets and organic beings possible. Every atom of calcium in your bones, of iron in your blood, was forged in the belly of a star that ended in such a blaze. The cosmic ashes of supernovae fertilize the galaxies, ensuring that each new generation of stars is born with a richer array of ingredients for planets and for life. We have traced the lives of stars from gentle birth in nebulae to either a quiet sunset as a white dwarf or a cataclysmic finale as a neutron star or black hole. But our exploration of suns would be incomplete without considering that stars rarely live in isolation. Most have companions or families of their own, multiple star systems bound in gravitational dances, or retinues of planets that circle around them. Our sun itself has a family. The planets, including Earth, and smaller bodies that formed from the disk of dust left over from the sun's birth. And many stars form in pairs or trios, locked in orbits around each other. To truly understand the nature of suns, we must also look at these relationships, the celestial communities that stars form, and the diverse planetary systems that have arisen around distant suns. Each star in the night sky is a sun in its own right, and many are far from solitary. In fact, most stars are born as multiples, two or more suns bound together by gravity, orbiting a common center. Imagine a binary star system, two suns locked in an elegant dance, circling each other over years or centuries. From a distance, they might appear as a single point of light, but up close, each partner star swings through space in response to the other's pull. Some binaries are widely separated, each star carrying its own retinue of planets. Others whirl so close that they can trade gas, or even, in extreme cases, merge into one. In a triple or quadruple system, the dance grows even more complex, with stars tracing intricate paths around their mutual center of mass. The universe is a grand stage, with every stellar configuration you can imagine. There are suns that eclipse one another from our viewpoint, causing their combined light to rhythmically dim and brighten, cosmic beacons signaling their orbital waltz. There are stars so close that they share a common envelope of gas, two stellar hearts wrapped in one glowing shroud. And there are systems where small companion stars orbit giant ones in distant loops, like tiny sparks flitting around a great flame. Around many of these suns, planets coalesce and circle, for planet-making is a natural companion to star-making. When a star is born from a spinning disk of dust and gas, the leftover material often forms worlds. Our own solar system is one example, a handful of major planets and a retinue of smaller bodies. And we have learned that planets are astonishingly common. We now know that planets accompany stars throughout the galaxy. Astronomers have discovered innumerable exoplanets orbiting distant suns, and they suspect that for every star we see, there are likely worlds in attendance. There are planets that cling close to their stars, scorched and locked by gravity, so that one hemisphere endures endless day while the other is in perpetual night. There are planets at just the right distances from their suns, the so-called habitable zones, where conditions might allow liquid water and the chemistry of life. Some planets orbit twin suns, experiencing double sunrises and double sunsets, their skies graced by two stellar disks. Imagine standing on such a world, with two faint shadows dancing on the ground, or on a world under a dim red dwarf sun, where the daylight is a brooding ember, and the stars' frequent flares paint the sky with sudden ruddy hues. Each planetary system is a story of creation, just as every star's life is a story. Some stars have giant guardian planets that shield inner worlds from comet bombardments, as Jupiter helps shield Earth. Others have planets in wild, elongated orbits, leading to chaotic swings of climate. Some massive stars might not host long-lived planets at all, as their fierce radiation and short lives can blast away or outlast any nascent worlds. But around the more common, steady stars, the red dwarfs, the orange dwarfs, the sun-like stars, there are surely many planets that have persisted for eons, perhaps even giving rise to life. Under alien suns, if life has blossomed, creatures might gaze up and see a sky tinted by a different color of star and wonder about the warmth that gives them life, just as we ponder our sun. For us, those other suns have been points of curiosity and imagination for as long as we've had eyes to see the stars. Only recently have we begun to detect some of their planets directly, to see the telltale dip in a star's light as an orbiting world passes in front of it, or to measure the slight wobble of a star tugged by the gravity of unseen companions. Each discovery is a revelation, proof that our sun and its family are not unique, that the cosmos is filled with solar systems. It humbles us, yet also makes the universe feel more intimate. A place where countless stars shine down on their own worlds, as the sun does on ours. Now, after journeying so far through stellar nurseries, fiery demises, and distant solar systems, we return our focus to our own star, the sun, and reflect on its ultimate destiny, and on what it means for us to live beside a star. And so we return to our sun, the star that has accompanied every moment of humanity's existence and that sustains all life on Earth. The sun today is a middle-aged star, steadily burning its fuel and kindly bathing our world in light. It has shone in our skies for longer than any living thing can remember, and will continue to shine for ages to come. But the sun, too, is mortal in the cosmic sense. Nothing in the universe lasts forever, not even a star. In the far future, long after our species and all we know may have turned to dust, the sun will begin to change. When its core can no longer sustain the fusion of hydrogen, it will respond by growing in size and luminosity. Our sun, so familiar and constant, will swell into a red giant. Its light will turn the color of copper and blood, and it will loom colossal in the sky. The innermost planets will be engulfed in its fire. Mercury and Venus will surely be devoured. Earth may meet the same fate, or be left a charred and barren rock, its oceans boiled away, its surface desolate and scorched. For any life remaining then, these changes will be catastrophic beyond measure. But likely, by that distant era, Earth will already be quiet and lifeless, or life, if intelligent and capable, will have found refuge elsewhere. The sun, once a gentle guardian, will become an inexorable destroyer of the very life it once nurtured. Yet even in this fierce transformation, there is a strange grandeur. As the sun's red giant phase reaches its climax, it will cast off its outer layers. Our star will shed its shining mantle, which will expand outward, drifting into space. For a short time, those cast-off layers will form a beautiful planetary nebula around the dying sun, a glowing testament to its passing glory. Future astronomers, perhaps from other surviving worlds or civilizations yet unimagined, might look toward our solar system and see a delicate shell of gas, like a cosmic flower blossoming and fading, shining in remembrance of the star that was. At the center of that nebula will remain the sun's core, now exposed and shrunken to a white dwarf. This final stage of our sun's life will be a small, hot sphere no larger than Earth, composed mostly of carbon and oxygen. The sun's very heart, left glowing like a lonely ember in the night. It will shine white and then blue-white, slowly cooling over the course of billions of years. The brilliance of the day that once was will recede into a gentle twilight. The white dwarf sun will illuminate the ghostly nebula for some thousands of years, but eventually it too will fade, perhaps becoming a black dwarf in the far, far future. The solar system will drift in darkness and silence. This is the ultimate fate of our sun, to swell in glory and then to divest itself of its brilliance, leaving behind a small, dense core that will quietly glow and then dim to darkness. It is a fate that the sun will meet far in the future, an inconceivable gulf of time beyond our lives. In knowing this, we find both melancholy and solace. Melancholy that all things we know are transient, that even the great sun will one day wither and leave the sky empty. Solace that we and our world have yet long epochs in which to live under the sun's light, and that when the end comes, it will be part of the natural order of the cosmos, the same finale that countless sun-like stars have already played out in the quiet reaches of the galaxy. And perhaps, too, there is a kind of triumph in this ending. The sun's final nebula will return its substance to space, enriching the interstellar clouds with elements that once made up Earth and us, and every living thing that sunlight ever touched. In that way, the sun's death will seed new beginnings elsewhere. Some of the carbon and oxygen from the sun's core might drift for ages and eventually become part of new stars, new planets, new life. As it has always been in the universe, one star's end is another's beginning in the endless cycle of creation. Now, stepping back from this entire journey, from the birth of stars in dark nebulae to the blaze of supernovae, from the quiet glow of the sun's youth to its fiery demise, we find ourselves contemplating what it means to be the children of a star. To live beside a star is to live in a state of grace between wonder and knowledge. We orbit a massive, luminous being that gives us everything: light, warmth, the very possibility of life, and yet asks nothing in return. Our ancestors felt the sun's power and worshipped it. They built legends and monuments to honor it. We, with all our modern understanding, have not lost that reverence. How could we? Each dawn when sunlight spills over the horizon, painting the sky in rose and gold, we feel the same awe that ancient watchers felt as the morning star ascended. In that daily miracle, night yields to day, cold yields to warmth, and the world is renewed. We know the science of it. The earth is turning, bringing us once more into the sun's light. But knowing takes nothing away from the magic of feeling it. Beneath the facts and figures, there is a simple truth. The sun is the source of our being. Every meal we eat is sustained by sunlight captured by plants. Every warm breeze that caresses our skin, every drop of rain that falls, is driven by the sun's heat, nurturing our planet. And our bodies themselves are made of material created in long-dead stars and powered by the sun's current light. We truly are made of stardust, shaped into conscious form and given the spark of life by a star's energy. In a very literal sense, we are children of the stars. When we say we are born of starlight, it is not just poetry, it is lineage. The elements in our flesh were brewed in stellar furnaces, and the energy that ignites our living cells is a gift from our sun. Our story and the sun's story are inseparable. Think of the connection. A baby born on a bright morning, crying out with lungs filled for the first time. Those lungs draw in oxygen that a star, billions of years ago, forged in its core and then cast into space. The baby's parents smile in the sunlight that streams through the window, sunlight that left the sun just moments earlier, having traveled across empty space to fall upon that new face. A chain of events spanning eons and light years has culminated in that ordinary, extraordinary moment. Starlight becomes life. The cycle continues. Standing here on Earth, we look up and see a blue sky by day. But beyond that blue lies the black tapestry of space and the brilliant stars. Our sun is one among many, and though we cannot see those others by day, they are there, distant and shining. At night, when our sun has set, we glimpse the wider cosmos of which our star is a part. We see the Milky Way's misty band, made of uncountable suns, and we realize that our little home orbits just one humble star on the edge of a vast galaxy. The humility of this perspective is profound, yet it does not diminish us. It elevates us. We are part of something immense and beautiful. The stars that speckle the night sky are our cousins. Some may have planets with beings who look up at their own sun and feel the same wonder. In the end, the story of suns is the story of creation itself. It is an ancient tale, told in the language of light and gravity. It began before we were here and will continue long after we are gone. But for a brief moment, we get to be conscious participants in this grand drama. We get to study the sun, protect ourselves from its tantrums, bask in its warmth, and dream under its light. Our lives, like mayflies, flicker in the daylight of this star. But while we are here, we behold the splendor of the cosmos through the window that our sun's light provides. As we conclude this journey, imagine once more the sun hanging low at dusk. The sky blazes with color, and the shadows grow long. In that sunset is a reflection of the entire epic, day turning to night as stars appear one by one, the cycle of light and dark that has guided life's rhythm from the beginning. The sun will rise again tomorrow, as it always does, bringing a new day. But even when it eventually rises no more, the legacy of its light will live on in everything it touched. We live on the brink of a star's fiery grace, taking our nourishment from its hand and daring to learn its secrets. We are small, but we are also a way for the universe to know itself. Matter that was once scattered across space, now gathered and alive, pondering the star that gave it life. In the dance of sunlight and shadow, we find meaning, comfort, and inspiration. Our sun connects us to the universe and to each other, a common star, binding all living things in a shared radiance. So when you next stand in daylight, feel that warmth and remember, you are heir to an ancient covenant between earth and sun. Every photon that touches you carries a message from that central fire, that life is precious and intertwined with the cosmos. Our world exists because a star shines. And in the atomic hearts of stars, in the silent roaring of their nuclear fires, in the gentle glow that crosses the void, the universe has found a way to nurture consciousness and wonder. This knowledge, this feeling, is humbling and uplifting all at once.
The Saga of Suns is indeed a cosmic poem, forged in light, breath, and gravity. It is written across the heavens in the glow of nebulae and the ashes of supernovae, in the rising of each morning sun and the eternal glitter of the night. It is a poem we are part of, every one of us made of star stuff and sustained by starlight. In knowing this, we find not despair at our smallness, but gratitude and awe that we have the privilege to dance in the light of a star, and through that light, to glimpse the eternal.